I would like to welcome Siddharth and would like to introduce him. Siddharth has graduated in graduation of BEEC from CU Shah College of Engineering. He has cleared the GATE examination and has also worked in academia at Darshan College for a year. He did his MTech, that is Digital Electronics and Ed Communication specialization from MIT Manipal in the batch of 2013. He has got total 10 plus years of experience and currently he is working in MediaTek India Private Limited. From last 6 years, he is working with the mobile processor team and working as a project manager for ISP team. He is someone who is a sports person as well, who loves to play table tennis. Today, he is going to brief us about the physical design flow in the field of VLSI.
Yes,
Siddharth, you may start the
yes.
session. It is all up to you now. Over to you, Siddharth. Welcome aboard.
Okay. Thank you so much. So is it audible now?
Yes, it is. Yes, it is audible.
Yes.
Okay. Okay, thanks. Thank you. So, like long back years, the VLSI was not very much familiar, with everyone. So now, as from last 5 to 10 years, it's been so much familiar with everyone, from the semiconductor fabs, when it's coming inside India. And so I just want to go through how this VLSI the flow is there inside VLSI it's a very vast it's a very vast subject. So what I would say in the VLSI there will be some front end and there will be a back end. So in the back end so the people will start coming from the back end starts from the synthesis. So synthesis, I'll just go through little bit of things and then I'll start my presentation. So let me just go ahead. So today's agenda will be I'll just give a brief introduction about the physical design flow and what kind of the challenges we could face. And later, we can go ahead with the question and answers. Okay. So first of all, what is physical design? Maybe when we were in the colleges, it was not familiar this name, physical design. So this is something, what I would say, it's like when you're writing a code, when you want to build something. So you definitely you'll go ahead with first thing you will be you will be writing a code. So now that code, when we want to translate into the physical chip, so that is called physical design. So so our input will be suppose it's a get level netlist. So inside that there will be some logical connectivities will be there in present of the inside the netlist. So how it is present inside the netlist, same it will be a replica in our design in our physical chip. So how the standard cell has been placed, how the SRAMs has been placed, how the wiring is has been done, how the physical wire has been done, the connectivity. So that will be present inside that will be present inside the GDS. So GDS is something related to graphic data streams. So which is it will be in the form of binary. So it's encrypted, we cannot see that, but we can you through the EDA tools, we can view what is inside the GDS. Okay, so this is actual our VLSI flow. So what happens if any customer comes with this frequencies or this many clocks or this much of function it has to be done, that chip we need to write some code and we need to write some we need to get some chip. So for this, from the specifications from the vendor or the customers, the designers, the RTL designers or the architectural designers. So they'll make some architecture based on the specifications from the vendor. What kind of architecture they want to go ahead. They will be building everything from the start in like I mean how what kind of CTS we want to use, what kind of placement, like I mean what kind of scenarios we want to use. So that thing will be taken care in the architectural design. After that, like the RTL designers will start their writing the languages, like I mean the register transfer language. So this comes under the Verilog. So like I mean when you like what depend on like the specifications requirement from the vendor, they will write down their codes. So from the codes, like I mean the physical design will now enter. Like from that code we need to translate that RTL to the like I mean Verilog, which is like the tool can interpret that language. So from there, like I mean, from the physical design, once like I mean, our everything is closed, like I mean, timing, congestion, everything which is as per the requirement, we have made up a software chip that is called physical design. After in terms of the software, it will go again. Like I mean, we need to verify. Like I mean, whatever the things we have done in the form of like software chip, it has to be gone through some verifications and some sign of criterias. After everything is clean, we can go ahead with the fabrication, like I mean fabs. So depend on like I mean whatever the nanometer we have designed the chip, right? Depend on that, like I mean the fabrication will start the process for the fabrication, and they'll go ahead with the what kind of package they need to use, what kind of testings they need to go ahead. So many other things will be there, and later like I mean we can close the chip. That is our actual VLSI flow. So inside VLSI flow, the main thing what I'm going to cover is a physical design. So physical design, like, so these are the steps, like part, as you can see, like I mean, partitionings will be there, then a floor plan, power plan, placement, clock tree synthesis, routing, and then there will be a timing closure. Like I mean, setup and hold, there will be a timing closure. So about the synthesis, what I told previously, like I mean, I'll just briefly explain what is synthesis first. So synthesis is something like, I mean, we are like, suppose there is a RTL code. Okay, so there like I mean we are writing in terms of like I mean if and else, like some loops will be there. So now what does the synthesis do? It will try to like I mean elaborate like I mean whatever the language they have written. It will try to come up with some related to its logic connectivity, logic gate. Suppose like I mean whatever the we have written. Suppose if any some if loop is there or something, and that comes under as a AND gate. So what synthesis will do, it will first try to elaborate that design. Now suppose whatever we have written, now it has elaborated, like I mean it terms of like I mean the logic gates, AND gate, OR gate, NOT gate, anything. After that, what it will do, like it will try to map that particular whatever the logic gates we have, like it has now the design has understand this is a AND gate, this is a OR gate, or this is some other gates. But technology perspective, it is not particularly defined which cell the synthesis has to use. So that is called mapping. So mapping means like I mean now suppose like we are going ahead with some like suppose it's a TSMC foundry. We are using the TSMC. So suppose for the TSMC, each nodes like I mean 2 nm, 3 nm, 4 nm, whatever, depend on the its each nodes. It will have like I mean they will have its like libraries. So from that library, particularly which cell we can use. So from that which AND gate or which OR gate we need to use, that will be mapping will be done inside after after the elaboration will be done. After mapping, we can say there will be a stage like somewhere like I mean DFT will be inserted. So DFT we are inserting in terms of like I mean DFT is nothing but like I mean it's a design for testability. Like whatever the code it has been written. So any chip, suppose like I mean it is going to be function. So for that there will be like I mean some set of modes will be there. Like there will be a function mode, there will be some scan mode. So function mode means what? Like whatever you have written the code and when you are translating it, and the design correctness will be done for that norm like function mode. But now this function mode, whether like I mean after one flip flop to the another flip flop, if anything is missed out somewhere, how will you test it? So that comes under like I mean the DFT. So how like I mean if we want to control, if we want to observe anything after each like beat, right? After each clock. So for that like I mean DFT will be inserted. So after DFT like I mean it will be in like we can say there will be some optimization will be happen in the synthesis stage. So synthesis optimization means what? Like whatever the cells they have used. Now optimization can be in terms of area also, optimization in terms of power also, in terms of timing also, it could be anything. So depend on that they will try to change the cells whatever the end get they were using. Now they want to use it for the better optimization purpose. So that is called now after this optimization we will dump a netlist. So that is called like I mean our first input for the physical design. So this is like I just brief you like I mean what is the synthesis actually does. So our physical design like I mean requires this many inputs like gate level netlist. Then there will be some SDC files. There will be UPF file. So UPF is unified file format. I'll explain each inputs in the later stage. So there will be some timing libraries will be used. There will be some physical libraries will be used. There will be some taclef which is provided from the foundries, and there will be a lookup table. So this lookup table is only for like I mean like how one suppose like I mean one cell to other cell, the metal connected in the chip, right? There will be a metal connectivity ideally in the chip. So how much like I mean the resistance and capacitance will be there, that will be we will get it from there. Yeah. So I'll just go ahead now like I mean the first input as I explained. So netlist is nothing but like it's like whatever like I mean we have written in the RTL, it will be come up with the gate level netlist. So how the logical connectivity of the cells are connected in the design. So that is called that info will be there in the netlist. After that, there will be another input which is called SDC. So this is called SDC is something related to the constraint file. It's a synopsis design constraint tool. So this is a constraint file. How you are constraining your inputs in your design. Like suppose as I mentioned, like I mean from the specs, there will be like written will be there from the vendor side. Like I need some 1 gigahertz frequency for the camera, or like I mean the CPU or GPU can be used for 2 gigahertz or 3 gigahertz. So depend on that, there will be some design constraints. So like I mean create clock definitions will be there. In the create clock, suppose like I mean there are some hierarchies in the modules. Like it cannot be a single module, right? Like so there will be some like multiple hierarchies. So multiple hierarchies. So there will be different clocks could be defined in the different depends on the design. So generated clocks, just generated clock means like I mean whatever our input clock frequency is there. So it could be multiplied by 2, it could be divided by 2, whatever is required depend on the design, we can generate like generation of the clock. Virtual clock. So virtual clock is something when it is required. I'll tell you here. Suppose like I mean there this is your one block. This is your second block. And
Sir,
this will
excuse me,
be
the lights are not moving, sir. Please.
Siddharth, what you are trying to show isn't visible. Like the blocks that you are mentioning, we are not
hmm,
able to see them. Are you showing any of your slides?
no.
Okay. So you are showing by any pointer or anything, but somehow we are not able to see the pointers. Okay.
Oh, okay. So pointer is not visible, it means.
Yes.
Uh,
Let me just help
It
from
shows
my end
only the
as
first
well.
slide.
Yes.
Let me change the pointer style. Are you able to see the tick marks, whatever I have done in the slide?
This is first slide only.
Slide is not
No,
changing.
He is not, he has yet
slide
not
is
changed
not
the
changing
slide.
and it is only first slide.
Siddharth,
Yes.
Only
are you on the
title
Oh,
first
slide.
slide?
I is it in the netlist? Like I mean the first written is netlist SDC.
Yeah.
No. It's
No,
the first slide
no,
only.
it is
Sir, this is the
your name
Word
in
file.
title.
Oh,
This
how
is the
come?
first slide only.
Oh,
This is
I'm
the
The
Word
slide is
file, sir.
not changed from the
uh
starting of the uh, this FDP.
because I
Okay.
just thought, Siddharth, that you were narrating something and after
Yeah.
that you will start the slideshow. So that was the reason I wasn't mentioning this. That very first slide has been stuck on the screen, but I just thought it is the way you
Oh
have
my
planned
God.
it.
Okay. Let me discard and let me just start again something.
Yeah, please, if you can. Yeah. Okay.
So now my
Yeah,
screen is
yeah.
visible.
Yeah. Now, better it would be good for us if you can give us a quick recap of slide 2 to 6 if you have reached to already slide
Sure.
6, right?
Okay.
Yeah.
Okay, fine. So I'm just turning off the slideshow actually. I don't know why the slideshow is not working properly. So this is visible, right?
Yeah. Is
Okay.
okay.
Okay, fine. So yeah, so I'll just go through whatever the agenda for me like we are just going through the physical design flow. That is our main goal for today's lecture. And there will be some challenges what we can face in when we are doing the physical design, and after that we can see the question and answers. Okay. So now as you can see, now it should be the third slide now. So what is physical design? I think everyone can see now, right?
Yes.
Yes, Siddharth, it is
Yes.
visible.
Now
Okay,
it's
okay.
slide 3 and
Yeah.
we are able to see that. Thank you.
Yeah, okay, thanks. So physical design, how I was explaining previously, there will be, it's a R2G things. Like R2G means what? RTL to GDS. So RTL is register transfer language till GDS. So GDS is our actual the formal, we can say a term of, from the software side the chip design has been done. That is called the GDS, and that software will be given to the fabrication to implement into the chip. So that is called the complete physical design. So now physical design, that it means we will be having some codes will be written, depend on how the customer depend on the customer's requirement. We will be writing some codes. From that code we will be translating that code into some gate level netlist which can the tool can understand. So that is called the netlist. After that in that netlist there will be at the connectivity of the cells, there will be some macros so this connectivity we are translating into a actual chip. How the standard cells will be placed, how much far it has been placed, at what layer the routing has been done. So these things in this info will be there in the GDS. In that GDS we will be giving back to the foundry owners, so that they can go ahead for making the chip. Okay, so this is our actual flow. If you can see, I had little bit told about this flow. There will be some customer requirement. Depend on the customer requirement, they will be writing some specifications. So from the specifications, it will be it will be going for the what kind of architecture we want to use in the design. There it will be everything. It can be what kind of the clock architecture, what kind any architectural dependencies, it will be discussed in the architectural design. After that they will go ahead for the functional and logic design. So functional and logic design is nothing but it's a RTL. So how they are writing the codes in the RTL language, so register transfer language. So that is called the tool can the RTL designers, depend on the customer's requirement, they'll write some code. From that code we will be circuit design is what we are translating that code into our tool can interpret what kind of the gate it is written. So that is called what we can say, it is a gate level connectivity between the two modules, or the full chip. After that, that gate level connectivity of the design, it will be translated into the physical design flow. So physical design, after physical design, in the physical design, there will be partitioning, floor planning, power planning, placement. After that, there will be a clock tree synthesis, routings, and then timing closure. After this is till like I mean it is done in the software, like I mean it's a software flow. We are not working physical design doesn't mean we are working on the actual, like I mean we are making a chip like a kind of PCB design or something. Here it's still in the software, like I mean we are using EDA tool, like I mean EDA tool vendors are there, right? So Cadence and Synopsys. So from the Cadence or from the Synopsys, there are few tools which we can go ahead for the physical design flow. So after whatever the design we have done, now that software, like whatever the chip we have made, that is working fine or not. So again, like I mean that testing will be there. That is called physical verification and sign off. After that testing is done in the software, we will be sending that GDS to the fabrication, like I mean, whatever the TSMC vendor, if it is there, any other, like I mean, who is making a chip from home, like I mean, we have taken the starting, like the PDK to everything. So that will be there. The chip will now the software is gone to the fabrication lab. After that, it will be checking the packaging and testing for that particular chip, whether it's a feasible to make that chip particularly without any like challenges or not. And then once it is done, it will be like the chip is finished. Like it's kind of tape out is done. Okay, so for the inputs like this, now I'm going ahead for the physical design perspective. So physical design flow needs some kind of the inputs. So from where these kind of inputs are coming, that I'll elaborate in the next like I mean slides. So the first thing is synthesis, like I mean gate level netlist. So when we say like I mean in the VLSI there is a front end and there is a back end. So in the back end, like I mean the back end starts with the synthesis. So synthesis, I'll just go ahead like I mean for 2-3 like minutes. So synthesis is nothing but like I mean what we are doing currently in the synthesis. It is something whatever the register transfer language we have written.
मैंने आपको पहले ही पूछा था.
Hello. Okay. So register transfer language, it will be written some in some of, suppose it is written in some if loop. Now, when we are translating that register transfer language to the gate level netlist, it can come up with something like I mean related to the AND gate, OR gate, or anything. Now, what so synthesis what it does, like it will first elaborate the whatever it is written. It will try to elaborate into terms of the gates. Now, when the it has found like I mean suppose if it is a AND gate, whatever the register transfer language is written, that is now converted to the AND gate. After the AND gate, which like mapping has to be done. So mapping means what? Whatever the vendor has given us some libraries, right? So in that it will be specific to 2 nanometer, 3 nanometer, 4 nanometer, depends on the nodes and depends on like I mean what kind of the how many layers are there. Depend on that there will be some AND gate variations will be there, OR gate variations will be there. So it will try to take some AND gate or OR gate depend on how it is it has transferred the logic. After elaboration is done and mapping is done, there will be some compile DFT stage will be there. So DFT is something like I mean when you are writing like one flop to other flop, some logic is going. But is it going fine or not? Who will check it? So there like I mean the DFT comes like to observe or to control the outputs of the flops. Like I mean to see like I mean so any design there will be some two modes will be there. So that is called norm mode and the scan modes. So norm is nothing but it's a function mode. How the chip is going to be function. So that is called function. It has to be correct. Like each flop output has to be correct. But who will check it? Like I mean each flop, suppose in your design it's a 5 million design. It's very difficult to check flop output to trace back, right? So for that the DFT comes into the picture. So DFT will take it like I mean it can write down some like some kind of RTL. From that RTL it will be translated to the logic. In that logic it will be like I mean controlling and observing the outputs of the flops. So after the DFT is done, there will be the optimization. So now optimization means what? It can be done in terms of area, power, or any like leakage. It can be anything. And after the optimization is done, we will get our netlist. So that is our first input, gate level netlist. So now I'm starting with that. So these are the inputs, like there will be a get level netlist, there will be a SDC file, there will be a UPF file. I'll go each input later, like I'm in the next slide. So there will be a timing libs, there will be a physical libs, there will be some tech labs. So which is take like I mean we have it will be taken from the foundry, from which like I mean suppose if it is a TSMC foundry, we will be taking the tech lab from the TSMC foundry, and there will be some table lookup. So I'll just go ahead. So netlist, as I told you, it is nothing but it's like a logical connectivity of the gates. How the design has transformed from the RTL to the gate level netlist. So we can see visually, like I mean the very low code, like I mean we will be visually see how the logical connectivity is done from one module to the other module or one cell to other cell. After that, there is another input which is called SDC. So SDC is nothing but like it's a synopsis design like constraint file. So this is needed like I mean when you want to meet the timing, like I mean from one cell to other cell, when the signal is going, it should reach in some within some time period. So those kind of constraints are will be written in this SDC file. Even like I mean suppose in your spec file. So spec is nothing but it's the specifications. So specification is given from like I mean the customer. How much like I mean they want to run the frequency, like what should be their frequency for the camera, what should be like I mean like GPU or CPU, whatever like I mean there will be having some there will be some constraints on which we want to run this chip. So first thing is create clock definition. So create clock definition is something like I mean at what frequency your like I mean frequent like your chip should be run. So that will be defined in the create clock definition. Generated clock means suppose in your design like I mean there are like I mean 4 5 hierarchies are there. So the clock is it could be possible for the another hierarchy of the design like I mean where it needs a divided clock frequency or maybe multiplied clock frequency. It could be anything. After that there is a virtual clock. So virtual clock is something like I mean when suppose if your block is having feed throughs. So feed through is nothing but like I mean this is some kind of input and output of that design where there is no logic inside that particular design. So some one block is talking to another block, suppose, but it is bypassing through some other block also. So if it is bypassing, right, it is going through that block, but there is no logical connectivity inside that particular block. So that point of time to define like I mean there will be we need to define like I mean what at what time it should the signal should come and what time should go out. That will be defined with the virtual clock for that particular block. So there will be some input delay, there will be some output delay. Input delay and output delay is something, suppose like I mean, one block is there. There will be some input and output for that particular block. Now that input and output, at what time the input should come to that particular design, at what time it should go out from that design. When you are running that block, right? At block perspective, like I mean, you don't know when the input is coming because you have not like segregated all like chip in it's not flattened design, it's a hierarchical design. So that point of time to just to give some estimated amount of time we will be giving the input and output delay. So after that there will be some max transition limit, max capacitance limit, max fan out limits. So like a clock latency, so latency is something like from the clock port, like I mean from the generation of the clock to your clock pin of the flop, how much time it is taking, that is called latency. Suppose then clock uncertainty is something like I mean clock edge, like in the real world like I mean clock edge cannot be coming as how you are wanted, like I mean exactly at what time. It there will be some deviation in the actual physical things. So that is called uncertainty. So that could be somewhere varying from 5% to 10% of your clock time period. It depends on that. Suppose like I mean your design is having a multi-cycle path. So like it is not feasible to close the time for that design uh, like in one cycle. So that needs a multi-cycle path. So we need to define that. So there could be possibility in the design where like, I mean, it's a two different clock domain where you don't want to check your timing optimization or timing calculation. So for that, like, I mean, you will be giving some false path. So all these infos will be there in the SDC file. After that, there is another input which is called UPF, so Unified Format. So what it does. So now, like, I mean, as it's a low power design nowadays. So we will be having like, I mean, multiple power domains. Why we are having a multiple power domains? Because like, I mean, suppose we don't want, suppose some function in the chip, it is not running at some particular point of time. Why we want to like run the entire thing? We can shut it off. So for that, like, I mean, we have not, it's in the low power design. It will be something related to the multi-power designs will be there. So those infos will be there in the UPF file. Then like from the like different, like suppose different clock domain is the, suppose different voltage domain is there. So one domain to another domain, different voltage will be there. So we need to use kind of level shifters or some isolation cells. So all those things also it will be there in the UPF. Now another input is timing libraries or logical libraries. So logical libraries means whatever the cells you have used in your design, like AND gate, OR gate, anything. How is the functionality of that? How like, I mean, suppose if it is AND gate, the like if there are two pins A and B, how much time the A is taking, how much time the B is taking, how much inside the cell is taking the delay, all kind of info. Like, I mean, how much like the max run limit for that particular cell, what could be the max fan out limit for that particular cell. So that info will be there in the logical libraries. After that, there is another input which is called physical library. So dot left. Dot left is it's physically any kind of the info related to that particular cell or macros or anything. It will be written in that dot left. Suppose AND gate is there. Now AND gate is having like, I mean, two like three pins, two input and one output. So how many inputs are like, how many inputs are there? What is the output? At what layer the input pin is there defined? At what layer the output pin is defined for that particular, when it is comes into the physical things, power and ground for that particular cell. So all those things, what is the dimension of that particular cell? So those things will be there in the dot left file. After that, there is another input file which is called a technology file, techlef. So techlef is the most important thing in the like PD, because like, I mean, whatever the foundry we are going to fabricate, like, I mean, the chip. So that input has to be there from the technology file, like how many metal layers will be there in the design, how many like what could be the width of those metal layers, what should be the spacing for those layers, what should be the pitch, how many what kind of the vias are available. Via is something related to like, I mean, suppose there are two metal layers, they are connected. So how it is connected physically, that is that joint is called via in the physical design term. So those kind of infos will be there in the technology file. Then there is a table lookup, TLU. So TLU is something when one net, like one wire, is connected between the two cells. Now physically, when we see that two connection between, like, I mean, the two cells which is connected to each other, right? How much resistance is there? How much capacitance is there? So those things, information in it, indexing figure will be there in the lookup table. So till now we have gone through just like, I mean, what are the inputs required to run the PD, like physical design. Now the first stage, as I mentioned in the physical design, the first step will be the floor plan. So floor plan is something how much you want to decide your like I mean your block area. What should be like I mean suppose now as I told like I mean in the previous nowadays it will be a hierarchical design. It's not a flattened design. So hierarchical design means what like I mean there will be like in the full chip there will be some IPs will be there. Inside that IPs there will be some blocks. So now when we want to run physical design for that particular block, what area we need to give for that particular block? Who will tell us? So that will be given from the RTL designers, whoever has actually written the code. So they will have the exactly info like I mean suppose like there are like I mean 1 lakh instance count is there, and that area whatever the 1 lakh instance count is there, how much area it is occupying. So that info they will have it. So from there we will decide depend on like I mean the criticality of the block. We will decide the utilization for that particular block. So utilization is something how much your logic area inside your total area of the block. That is called utilization. So some critical designs, there could be utilization could be like I mean starting unit it could be 40%, 42% also. If the design is not very much critical, like in terms of timing, then they will push their limit for the congestion. They will try to increase the utilization. So utilization, suppose if they are increasing from 40% to suppose 60%. So 60% means the area is now reduced. Now 60% of that particular block area is covered with the logic. It means like that 60% is covered by that logic. So that will be defined in the floor plan. So when we do the IP, suppose if there is a IP, so here you can see there are 3 type of IPs are there. So in a single IP, there will be some different number of the blocks will be there. So for the top floor plan, there are 3 types: abutted, non-abutted, and there is a partially abutted. If you can see in the abutted floor plan, the 2 blocks, there is no channel in between. Like suppose from one block to other block, some channels are going. We have not kept any kind of the channel. So what it means, it will try to help you in terms of the area for the total particularly chip. So here we have reduced the area by doing abutted for the floor plans, but it cannot be feasible entirely in the design. Suppose if it is a asynchronous design, it could be possible. But suppose if it is not like it is a synchronous blocks, like I mean one block and another block from the top clock port, it could be possible like I mean these 2 blocks are completely like talking to each other. When we do a flatten the design, when we flatten this, it could be possible from one flop which is going from this block, it is going to the another block the flops. So during that time, like we need some channel like I mean for the clock routing from the top perspective. So this is called a non-abutted. So non-abutted means what, like I mean entire blocks in the chip, like they are synchronous in terms of like I mean each other, and like I mean from the block tops clock perspective and the inputs. And the third one is partially abutted. So normally we will go ahead with the partially abutted. So that like partially abutted somewhere wherever it is not required. Suppose like I mean 2 blocks are they are placed adjacent, but there are no connectivity. Then we can abut it, because ideally we are saving that area. Because here like I mean one, like if you are saving the area in terms of, because we are building like when we are giving a chip to the fabrication, right? So what happens like I mean there it is in terms of the silicon like we are calculating. So whatever the number of area is more, in terms of that like I mean in the single wafer the number of chips will be less. Your it's like it's the cost of the chip will be more. So wherever is possible we will go ahead with the partially abutted, and wherever we want to give the channel we will give the channel. So today, like as I told, I'll because physical design is a very big like it's an area. So top related things I'm not covering much. I'm covering mostly related to the blocks, because like I mean once because top also it will be nearly similar how the block is like doing the physical design. Only few changes will be there in the top, that's it. But ideally it's a bottom to top approach. So bottom means what? It's a block. So once your block is ready for the physical design, you can go ahead for the upper layer like that. So for the block perspective, when we are running the floor plan, what stages will be there? So that I have covered here. Like there will be some side, so we need to define some side rows. There will be some tracks, voltage we need to create, voltage area creations. We need to place the input and output ports. We need to place the macro placement. Then there will be some well taps and tap cells, and there will be a power grid. So I'll go ahead in depth for the next slide. So site row is something, as you can see in the image, these are called the site rows. When you are like, I mean, when you are starting your floor plan, right? So you will see this site rows. So these site rows will be given from the tech left. Like how much, like, I mean, each, like whatever the tech left is using the standard cell height. Okay. So that height has to be fit into one particular row. So depend on that, like, I mean, there will be some railing. So now in your standard cell, if there is one VDD will be there and one VSS will be there. Now, in your design, if you can see, there is like, I mean, there is this arrow mark is there. So it is flipped row. Why we are using a flipped row? If we are not going ahead with the flipped row, then what will happen? I'll show you here. Suppose there is a standard cell rail in which, like, I mean, the standard cell VSS is here and VDD is here. Now the second row, when we start the side row. So here again, there is a VDD and there is a VSS. So what will happen? How, like, I mean, you will be able to draw your power mesh. It becomes very difficult. So what we do, we will flip the second row. So what will happen? This green color will come back to the here and this red color will be come back to this side. So it means two VSS is connected together and two VDD will be connected together. So that, like, I mean, power mesh will be given throughout the design equally. After that, there is a tracks. So what does it mean, tracks? So if you can see in the image, the dotted line is there. It's like pretty much difficult to see, but like, I mean, there is a dotted line here. So dotted line is something related, it defined as a tracks. And this dotted line, like, I mean, when physical route happens, so your physically routing the net will be exactly in the center of this particular tracks. So whatever the wire we have drawn, it will try to take the tracks exactly in the center. So that is called pitch, like from one track to the another track. That is called pitch. So this will help the tool, like, I mean, how to like go ahead when they want to connect physically, like two cells. So there is another, like, I mean, what we are doing in the floor plan, there is a voltage area creation. Voltage area creation, it means suppose if there are multiple power domains in the one block itself, how you are going ahead, like, I mean, for those multiple power domains, like, I mean, if the signal is switching from one power domain to another power domain from this in the same block, how we are going to take care of those things. So again, like, I mean, there are two things are there, abutted voltage area and non-abutted voltage area. Because, like, I mean, low power checks, we need to check at every moment. Suppose the signal is traveling from the off domain to the always on domain. What kind of the buffering we need to use? Like in the from the off power domain to the always on power domain. Suppose if it is going from the always on to the off domain, what kind of buffering we need to use? So depend on that, like, I mean, there is a abutted and non-abutted. Like, I mean, if we want to go ahead some buffering in between the two voltage areas, right? Then the non-abutted we can go ahead. After like this voltage area creation is done, correct? So after that, we will try to place the input and output ports. So suppose if there is a like so and there are some 500 input and output ports are there. Now all those ports, it has to be placed on the tracks. If it is not placed on the track, right, you will come up with some DRCs and all that. DRC is something related to, like, I mean, design rule check. To design, like, your chip has to be perfectly fine with some certain rules. So those rules we have to follow up. So that is called like design rule check. So it has to be perfectly placed on the tracks. Suppose like there are clock pins. So it has to be defined like in the higher metal layers. So that like your like the skew balancing and all will be very good. Any like input and output, if you are placing, it should not be overlapped. Like on the same metal layer, if you are placing two ports, ideally like it's a short circuit. So that is called like we need to take care those things. After the input and output placement is done, we will be going ahead for the SRM placement, macro placement. So macro placement is something, suppose like one block to other block, there will be some signals which is connecting from one block to the other block. So depending on that, that knowledge will be there with the RTL design engineers, like how the one block to other block it is talking. So depend on that, how the ports will be going to place. That also it will be given from the guidelines, RTL guidelines. So how the ports are communicating to the macros and to the logic. Depend on that guidelines, like we will try to place the macros inside our design. So we need to take care some of the things while placing the like macros. It should not be like overlapped, or like how one macro, if there are like possibilities, there are connections which is talking from one macro to other macro. We need to try to place those macros nearby. Otherwise, it will be difficult like when you are resolving the timing. Suppose like the ports should be facing towards the core area. So that things we need to take care. So and like suppose like two macros, pins are facing each other. Each macro will have their own set of ports, right? So those ports like it has to given some route, like some channel, so that like the routes can go and connect to that macro. After that, we'll be placing like this called like AND caps and well taps. So AND caps and well taps are the physical cells. Ideally, there are no, in terms of logical connectivity, there won't be any logical connectivity. But why we are placing this? So tap cells is something you might have heard like latch up issues. So latch up is something like when the CMOS like suppose input or output is going beyond VDD or going lesser than the VSS. So there will be some low impedance path from like, because in the CMOS there will be PNP and NPN will be there, right? So there will be some low impedance path will be there. So that low impedance path can failure the chip. So to prevent that, we will be inserting the tap cells. So these tap cells will be a part of our like whatever the physical like logical libs or physical left, whatever we have received from the vendors like TSMC, it will be there. So how much distance we need to place, that also it will be written in the file. So depend on that interval, we need to place that tap cells. So here, these are the tap cells you can see in the image around like the macros we need to place or something. It will be depend. And the AND caps. So AND cap is something where like you want to prevent your standard cell should not place outside that design. So that is given like boundary. It's a kind of boundary. Once you once the end cap is placed, your standard cell, when the placement will place the tool, the standard cells, it will check that there is a end cap. It won't place outside that. And it will help in terms of the fabrication also. Like because like end cap is not a logical, like as I told, like it's not logical things, right? It's a physical cell. So when we are doing for the fabrication at that point of time, suppose like if for the lower technology nodes, like it will be like very much difficult. Like when the fabrication is happening, it can damage the cell when it starts fabricating. So first row we will be giving it to the end caps around the boundary. After that, power planning will be done inside your floor plan stage. So power planning we will be doing before our like the placement is going to run. Otherwise, like what will happen? Like how the standard cells will place in the design. It can place like somewhere like suppose like some always on logic is required. So wherever the suppose one block is there which is off domain. Off domain means what? Like there will be some power switches will be there. when it is not required to turn on that block, it will be off. But there are chances that from that block, the signal which is traveling from that block to the other block, that block is on. So that point of time, some logic which is placed inside this off domain block, it requires some other power stripes, which is called always on power stripes. Like it's a, so that particular, if the power planning is not done properly, the standard cells placement would be difficult. So we will be going ahead like I mean for the power, this power planning. Depend on like I mean how much that particular block requires the current density. Depend on that we will be doing the PGB versions. Like I mean how much like power stripes it is required, how much dense it is required, the power stripes, power and ground. So depend on that we will be doing the power planning. After that, what is called like I mean the good floor plan. So these are the checks. So if you can see here, the ports all the ports, it has to be placed properly. There should not be any overlap. There should not be any off tracks, anything. Any macros, like it has to be placed as per the guidelines, because like I mean the designer knows like I mean how the net connectivity is happening inside the design. Physical design engineer won't be knowing the connectivity things. So that will be only known to the RTL designers. So we need to like follow the guidelines in some aspect. If we are not following it, it's okay. But like I mean, it has to be normally like I mean, 90 to 95% we will try to follow the guidelines. After that, there is a voltage area like I mean placement as per the connectivity. Then your power grid, whatever you have placed, like you have created, there should not be shorts or opens in that design. And there is the utilization. So utilization, what I described earlier, right? If it is a 60% utilization, means 60% of that particular block area is occupied by the standard cell logic itself. So that is called utilization. So it should not be very high or it should not be very low also. So that is called checks for the good floor plan. After that, we'll go ahead for the placement. So placement is something like once your floor plan is done and the like power stripes has been created. So how the this power straps will supply the power to the cells depend on that. Like I mean, try APR tool. Like I mean, APR is something automated like automatic place and route tool. So we are not like suppose it is a 5 million instance or 1 million instance, something whatever. We are not going to place each cell like manually, right? It is done by the tool. So tool will try to place those logical cells which are connected in the netlist, logical connectivity. It will try to describe in terms of the physical now cells. So physically now the cells will be placed in the design. So inside placement, we will try to cover up like I mean how much congestion occurs, how much like I mean what is the timing that we need to see. Because suppose like I mean there are cells which are like communicating to each other, but those cells are placed very near and those cells are like I mean many connections are there. So what will happen? When the physical routes will happen, right? That point of time there will be a short circuit. There will be shorts. So it becomes that is called congestion. It becomes very difficult like I mean to go ahead with that critical like I mean congestion, and definitely it will impact the timing also. So inside placement, there will be two type of placement will be done. There is a global placement and there is a detailed placement. Global placement is something like, I mean, as per the connectivity, the tool will try to place that cells. It will try to check the cell overlaps. It will try to do some kind of like things, but it won't be 100% accurate. It will try like, I mean, if the two cells are connected to each other, the cell won't be overlapped to each other, but it will try to minimize the net length between the two cells, so that like I mean there should not be any timing failure should happen. Now the detail placement is something related to when the global placement has been done. though the cells are not overlapped to each other and the minimize the net length has been done. But it could be possible where the congestion is there because there will be some so now in the lower technology nodes, what happens AND gate, OR gate, inverters. So ideally these three are the different three gates, right? These all three are different gates: AND gate, OR gate, and inverter. But suppose when we are coming to the physical design, there is only one cell which does the same thing what these three cells are doing. So that is called AOI gate. AOI, so AND or invert. It does the same functionality, but now we are using this one cell, but it requires many number of pins. So if many AOI cells are placed very nearby, correct? So what will happen? Like the routing requires a physical route, it has to be some empty tracks has to be there. But now the cells have been placed, but there is no sufficient routing spaces available. So that is called in the detailed placement, it will try to take care those things at some limit. It will not try to 100% clean because tool cannot clean. It's a tool, right? We need to give some inputs to clean that congestion or timing. So now, as I mentioned frequently, there will be some congestion will be there. So what is called congestion? So if there are number of the available routing space in the design, it is lesser than the required routing availability, then that is called a short circuit. That is called a congestion. So congestion could be occur because of the more number of standard cells placed in the small area, or maybe near to the macros and we have not given sufficient space near to the macro, like channel, if the channel is not given. Suppose in the optimization stage, so many two different modules place the SRAMs we have placed very far, but they are actually connecting to the each other, communicating to the each other through the some logic. So it will try to pull that logic. But now if it is placed far, so what will happen? Tool will try to clean the timing, it will try to add some buffers to meet some tran criteria. As I mentioned in the earlier, there will be some max tran, max cap, max fan out. Depend on that, it will try to add some kind of buffering or something it will do. So that can create a congestion. So how to fix that congestion? So what we can do, we can there will be some set of options in the placement tool itself, to take care those congestions, uniquify something, or maybe the density driven, or maybe maybe using of the some blockages, hard blockage, soft blockage, or partial blockage, where a partial blockage is something you need to give some particular area where you don't want much number of cells to be placed. Like suppose if you have given 40%, so whatever the coordinate you have given, so that will be taken care in that, 40% only cells will be placed in that region. So those kind of things we need to take care. So any high pin cell count is there. Suppose as I mentioned, AOI cell. So AOI cell will have 8 to 9 pins. Suppose AOI cells in your design to in the synthesis, suppose to area reclaim, they have used more in a 1 million design, suppose it is more than 2 lakhs or 3 lakhs, then the number of pin, the net requirement is more, though the cell utilization is less. But the routing tracks availability is not there now. So those things we need to take care. High fan out pin, suppose some cells are there. We need to give the feedback to the synthesis team. We cannot use so many same type of cells. Or at the end, we can modify the floor plan. Floor plan in terms of the SRAM placement, with the macro placement. That we need to take care. I hope my slides are visible, right? Because there was some disconnect. Hello?
Visible, sir, completely.
Yes, sir.
Okay. Thank you. Okay. So now what is called once your placement is done. But how can we say our placement is good or bad? So as I mentioned, the congestion, right? So congestion is something in the physical design. There is a hotspot. So hotspot, it will show in the design in which area, like there could be like shorts can come in the future when you route the design. So depend on that hotspot number, it has to be acceptable number. It cannot be very high. After that, after placement, we will go ahead one round of routes, like just to see how many signal shots can come up in that placement. Here we have not done the CTS till now. We will be checking just for our purpose, like I mean, the placement is done properly or not. And then there will be a setup time. Now in the placement stage, we will be checking only for the setup time. We will not be checking like the hold time, because like I mean, hold is like depend on the clocks, and clock is not routed till now. So we will be checking only setup time. And about this timing, right, I'll be telling in the next slides. So now after that, like I mean, there is a stage which is called a CTS. So clock tree synthesis. So now, like I mean, whatever the placement tool has done the placement of the cells, right? All those flops, that's in this any flops or latches or anything, it requires a clock input. So how the clock will be given to that flop? So that will be deciding here in the CTS, clock tree synthesis. And this is a most impacting, like I mean, the thing in the physical design, this entire stage, because it consumes 30 to 40% of the total chip power. So like as in the it's a low power design, like I mean 30 to 40% of the chip power, if your CTS is not built properly, then like it's going to be adding more number of buffers. It could be possible, or maybe like your timing is not at all able to clean. So it's a failure of the chip. So for that, like I mean, what kind of goals we need to keep take care like while building a CTS. So for that, like I mean, insertion delay is something related to the latency only. As I mentioned in the SDC file, there is a latency, right? Max latency. So this is called also similar to the insertion delay is something related to the latency. How much time it is taking the clock to travel from the clock port to the first flop or any flop. How much time it is taking. It should not be too much high. Like it cannot be higher than your clock time period. It's as simple as that. Even it cannot be 50% of your clock time period. You will not be able to meet the timing. After that, like I mean, how much it is balanced, how much your clock tree is balanced, because once if there are paths, one flop to other flop, has to be balanced. Skew is something like I mean the clock pin from there, like I mean the launch flop, how much time it is taking, and from the clock pin, clock port to the capture clock pin flop, how much time it is taking. So that is like once you subtract, you will get the skew value. It should not be like very high or very low. Then your like logical DRVs. So DRV is something related to the tran cap and fan out. So as like I mean it's a signal as any cells, suppose AND get or get anything, the output pin or the input pin. It depends like tran cap and fan out, right? So similar to that for the CTS also when we are building. So any clock buffer or clock inverter we are using. For that also, like I mean, there will be some designated values. Like I mean, it cannot cross that value. If it is crossing that value, it will be like failure of the chip. And what kind of like a buffer and inverter we need to use in the design, at what layers we want to use, what kind of NDRs we need to set. So NDR is default rule. So non-default rule is something the clock width, right? So when we are like there is clock is something related to like I mean when in the physical aspect it's a kind of wire which is going, right? So that wire, it should not have any kind of the crosstalk or noise due to like any switching between the adjacent nets. So for those things to take care, we need to set the NDR rules like double with double spacing or something. So that like I mean double spacing we are giving from that particular clock net to the other net, whichever will be placing. It will be placed after two tracks. So there will be two tracks. It will be empty in that very simple clarification. So now here there is so before CTS and after CTS, how the design is looks. Like suppose from the clock port, it is going the clock pin of the flops like this. Now after CTS, it is balanced like this. Now, like as I mentioned, like I'm in target latency and target skew. Correct. So if you remember when I was speaking, like I mean there will be clock latency, how it is measured from the clock port, how much time it is taking to reach to the first launch flop. That is called latency or insertion delay. And the subtraction of these two, N5 and N4, that is called skew. So that is we have written here. So in the physical design, like I mean skew has to be balanced. It cannot be like anything. Like it cannot be very high. If it is very high, right, becomes very difficult. Like
આપણ આમાં આની અંદર આવડું છે રાખી દેવાનું છે
Dear participant, please you turn off your mic.
Okay, so they like when we are building a clock tree, right? There are like I mean different types of the set of the clock trees are there. Like which clock tree we need to go ahead, that will be like that info will be given to the architecture. Like I mean who is building that design, like how it is deriving. So whether to go ahead with the balanced clock tree, whether to go ahead with balanced binary clock tree, H tree, there are so many other clock trees also like fishbone or some other like clock trees. So what are the differences? Like I mean, as you can see, balanced tree means what? It will try to balance the skew between the two flops, which is it is trying to communicate. It will try to add the buffers. These are the buffers, clock buffers. When it is balanced binary means what? The number of sinks will be equally distributed. When there it is called binary. When it is called H tree, H tree is something like, as you can see, if it is here, if it is your clock port, from the clock port, one flop is placed over here, suppose, and one flop is placed over here. The time traveling distance from the clock port to reach to that flop, it will be equal time. So your skew is 0 in that sense, ideally. Here we are talking about the ideal scenario that H tree will support you for balancing your skew. But now there are some limitations. Like, I mean, we cannot use blindly any of the clock trees. If it is a very high frequency and the number of flops are less, we can definitely go ahead with the H tree. But if your instance is multi-million instance, like I mean 5 million, 7 million, something, that very big block will have the number of flops will be more. It is the flops are not equally distributed, like the placement of the flops are not equally distributed in the design. It can be placed anywhere in the design. It becomes very difficult for the H tree, like I mean to build a clock tree for with the H tree. So that point of time, we may go ahead for the balanced clock tree. That is the easiest way. And there are some pros and cons for the both things, because like I mean H tree requires like I mean the nets route will be more. So it means your wire load is more. That means your dissipation of the power is also more. Even though like I mean the flop is communicated to here and here, if it is here and here, okay. So what will happen? Like I mean it will try to communicate. Like it should try to keep the minimum way if it is a balanced clock tree. But here it is not a balance, right? Here it is H tree. So H tree means like I mean now it will go to some certain value and then it will come back to that flop. So your routed path is now it's very much high. So because of that, your power will be more dynamic power. So what kind of the exceptions we need to give when we are building a clock tree? Like I mean, tool needs some kind of data. Like suppose in your block, suppose there are 5 clock trees, like 5 main clocks are there. Okay, so how to balance what flops are going to which design, that should be taken care in the CTC file, clock tree constraint file. So that will be having the info how it is balanced between the two flops and the data balance. Data balance is for the gals. So gals is something related to globally asynchronous, locally it is synchronous. Here we are talking about the one block, but there could be chances like one block is talking to the other block. In the full chip level, it is called as a, it's like it's not now uh, like say like it's when you're building a clock tree for the block, it is taken considered as a like it's a outgoing port. But when you're talking about the full chip, now it is like it's a same clock power domain. So it has to be balanced. So those balancing will be taken care as a gals, and that will be defined in the CTC that this logic has to be placed near to the ports in that way. So there are some exceptions are there: non-stop pin, stop pin, exclude pin, float pins, ignore pins. So non-stop is something like nowadays for the low power technologies there will be clock gettings as will be there. Like when you want to turn off some logic in the design, particular logic, you will be turning off from the clock gating. If enable signal is not present, then it will be like that particular domain is closed. So that is called like non-stop. Like clock gating is not your stop pin for the flops. Like clock should reach to the flop, not to the only clock gating cell. So that is called non-stop. Stop pin means when you want to stop your clock building. That is definitely a clock sync of the flops. Exclude pin means suppose in your design in the clock path, if there is a mux, because as I told in the starting, there will be funk mode and there will be a scan mode. So scan mode, how we will like check how we can observe or control, that is through the mux. So that select pin of the mux, it should be excluded, like because we are not calculating timing or calculation from that mux, right? Now there is a float pins. Float pins means if in your design, if there are suppose some SRAMs are there. So those SRAMs, inside that SRAM or inside that macro, the clock frequency might be different. So it requires some specific some special kind of insertion delay requirement. So for those kind of things, we will be need to specify in the float pins and ignore pins. So it could be like for the false path. After that, how we can see that it is a good CTS. So again, when you're doing the placement and when you're going ahead for the CTS, after the CTS, the U rate jump, utilization jump, it cannot cross more than 1.5%. If it is crossing more than that, it means the number of the buffer addition, clock buffer or the clock inverter has been more. If it is more, that means your CTS is not built properly in terms of suppose if there are 1 million design and there are 50 flops are there in the design. So for those 50,000 flops, how much buffer is required to build, that estimation has to be there. We cannot have the exact value idea, but it should not jump when it is finishing, it should not jump 1 to 1.5%. After that, there is we need to see the hotspot again. After CTS, we need to see the congestion also. And we need to see setup and hold. Now, it's now as the CTS has been built. So clock tree has been built. So we can see the setup and hold timing. It has to be in some moderate range. It cannot be very high. It cannot be definitely clean. Definitely it won't be clean because we have not done any kind of the data path optimization. And we need to see the DRVs. After that, there is a routing. So routing is something, as I told previously, it requires how the physically connection is happening between two cells. It requires some routing, metal layer routing on each layer. Suppose the design is having 15 metal layer. How one pin to other pin it is trying to communicate, that we need to see, because here the exact scenario will come up as a timing scenarios. If it is routed on the lower metal layers, the resistance will be high because the lower metal layers, the thickness will be very low, right? So here what will happen? It will be difficult to clean the setup time. So it has to be moderate neatly routed in terms of like the layers, like like metal 7, metal 8, metal 9. It depends on that. So like what are the goals of the routing? So it has to be like the minimum wire net. First goal is that, right? Then any congestion is there, it should be trying to resolve that congestion. Then there will be suppose how many number of the layers are there, depend on that, and how many number of, like, if it is detoured net, it will impact your setup and it can impact your hold also, because it could be possible where uh like not meeting up the timing criterias, and it could be possible it is failing with the max tran, max cap, anything, and it has to be minimum DRCs. So DRC is design rule check. Like there should be something like spacing related rule will be there, width will be rule, length will be a rule. It cannot have minimum length. There has to be some minimum length requirement for the routing. So for the routing, it has the routing occurs in these 4 stages. There will be some global routing, then there will be a track assignment, then there will be a detailed routing, and there will be a search and repair. So if you can see in the image, how the cells have been placed, depend on that, the connectivity, it will try to assign some nets on some layers. But here it won't see the congestion. Like it could be possible, some 2 metal layers are drawing, like it has been drawn in the same. Here it is just assigned. After that, there is a track assignment on particularly what track it has to be placed, like it has to be routed. That info will be here. Because track assignment will go ahead with the timing aspect also. In the global route, it won't see the timing scenarios, but in the track assignment, it will check a little bit of timing also. After that, there is a detailed routing. Now, detailed routing means now it is an exact connection between the two cell physically. So here it will try to check in terms of when it is doing the timing optimization. Suppose 2 cells are placed very nearby, but in the global routing, it has tried to for the minimum length, it has tried to cover up minimum length. But in terms of timing, we have sufficient amount of the time between these 2 cells, even though if the routing happens little bit detoured, because other cells which requires a critical time, they have routed here. So that point of time, detailed routing will check through the timing also. Like if it is not required, like timing is not very much critical, it will try to detour also in terms of by keeping in mind max tran, max cap, everything. And then it will try to search and repair. Like so it will suppose if congestion is there in the design, it will try to resolve that congestion in some iterative loops. So that thing I have written everything in the next slide. As the timing is very less, I just explained you what it means, like global routing, track assignment, then detailed routing. Everything I have explained here. And then there is a search and repair. After that, there is so filler cell insertion. So filler is something now your standard cell has been placed. Between that, there is a one site space is there. So what should be done? Your annual continuity is not there because of these things. So to meet the annual continuity, filler cells we will be adding. So this filler cell is kind of physical cell. It's not a logical cell. After that, there is a metal fill. So metal fill is something in any design, there are some certain rules. Like in your design, some routing layers, like whatever the nets have been routed in each net, there has to be some density requirement, that each design should be having some density it has to meet. Now, suppose in your design, everything is done, but it is falling off 2% of the routing metal density. So in that sense, what will happen? We need to add some manually metal fills in the design. So there are two metal fills are there, floating metal fill and ground metal fill. So floating metal fill is something it requires like it is without like it's a floating metal. Just a minute. Yeah. So floating metal is something like we are adding to meet up the design rules, but here it is not helping us like to remove the SI. SI is something signal integrity. So signal integrity is something like because of like some other nets switching activity, the victim is like having suffering from like some extra delay value. So to come up with that, like we will be adding some grounded like VSS stripes. So that is called grounded metal fill. After that, there is a timing analysis. So once everything is done, like now the routing has been done. So now to see the timing, there are two things are there, dynamic timing analysis and there are static timing analysis. Dynamic timing analysis is something like, when it used to be used very long back when the like because it needs suppose like suppose there are 100 inputs, so it requires like parallelly to check 2 raised to 100 vectors to check thoroughly like all kind of timing clean design. So nowadays like suppose we are having multi-million design, we cannot use the dynamic timing analysis for that. Like now it is come up as static timing analysis. So static timing analysis is divide like the path in terms of input port till the first flop, from first flop to the second flop, from the second flop to the output port, like it could be, and then there could be into output. It divides the number of paths in that way, and it does like parallel calculations for all these paths. So as I have frequently mentioned, like there is a setup and hold time. So what is setup and hold? So setup is something, if you can see in the image, before the clock edge comes, data has to be stable. So that is called setup. If it is not stable, that means setup is violated. After the clock edge, there has to be data has to be stable for some amount of time. So that is called hold time. So if it is not meeting up this criteria, right? All those like it will be having like issues. So this is the equation like for the reg to reg timing, like t clock to q delay, like how much time it is taking from this point clock port to the q pin, from the q pin till the combinational logic delay. It has to be less than or equal to for the total time period, like which is for the setup. It has minus t setup time of the flop, the capture flop. This is a capture flop. This is a launch flop. So FF2 is a capture flop. So capture flop, how much time it takes like to initiate. That is called a T setup. And T skew is something like how much the skew is there. For the hold, the same thing will be there, but it should be greater than the T hold of the capture flop and then the skew. For the hold, it does not depend on the clock time period. It depends on the clock, but it does not depend on the clock time period, because hold is like measuring on the same edge. If you can see below snap, this is like a launch clock, and this is a capture clock. So launch clock setup will be measured the next edge in the capture. But for the hold, it will be on the same edge. So for the same edge, it doesn't require the clock time period in measuring the hold equation. How to resolve this setup and hold? So like setup means like your time, as I told before the clock edge, the data has to be stable. In terms of that, it has to be faster. So we must need to try our data path has to be faster. Low VT we can use, we cannot, but we need to see the leakage also. We cannot blindly use like all kind of LVT cells. Then drive strengths we can upsize from D1 to D4, so that like your like it can drive to the longer distance. We can route on the upper metal layers, minimize the route, and then like we can this capture clock path, we can slow down that also. But this is at the last we need to do. Clock path we should not touch if there are scope in the data path. Same thing, vice versa for the hold. Hold we need to delay the clock path. Sorry, hold we need to delay the data path, and clock capture clock path has to be faster. And then there is like what kind of the challenges we are facing. So now as a physical design engineer, like our goal is to like to improve the PPA. So PPA is something like power, performance and area of the design. We are the one like like as the it's going to the silicon directly, right? So what kind of the chip cost should be there? It will be 100% like we have like the power like to control the how much power we need to give to each block, how much performance can be like the each block is having, the even the chip is having the performance, at what frequency it is having, what kind of the area, how much we can try to reduce. So the thing is like as we going forward like for the lower nodes, right? So what will happen for the lower nodes? Like it becomes the design is getting shrinked. So when we are comparing with the RTL design, code is still the same, right? But for the physical design, they have to do it everything from the scratch again. Definitely there will be something like to modify in the RTL, but it is like they don't need to write up everything like from the scratch. So always like like as a physical design engineer, I'm seriously proud on that. Like we will be having like the demand every time, because as a physical design engineer, anything is coming up in the design, we need to work from the scratch again. So there will be always like, and definitely we have the control in terms of the chip, how much area we need to give, how much performance we can achieve, how much power dissipation we can reduce. So all those things we have the control. So as a physical design engineer, I'm really proud on that. Like we are having that power to decide all those things. And yeah, so that's it. Like we can go ahead for the question and answer if there are any. Like I tried to cover up almost complete physical design flow, and I hope like everyone has understood what like like what is there in the field. So I'm here like I'm almost like 11 years I'm experience I'm having, and I'm doing these things from last 11 years. So working, yeah, definitely for as a physical design engineer, I'm really proud on that. Like we are having that power to decide all those things.
Yes, anyone is
And
having query, it's a good time to ask him. You can raise your hand and put up your query. Okay. Is there anyone with any queries? Siddharth, thank you so much. Huge and immense gratitude to you for taking out the time. I'm sure you would be very busy and it must have been really difficult to take out the time. And it was a very informative and great session. Knowledgeable people are writing also in the comments that they enjoyed the session and they learned a lot.
wow,
Thanks a lot,
thank
Siddharth.
you so
Thank you
much.
so
Yeah.
much.
Okay, thank you
Ye-
so much. Thanks everyone.
Yes, yes, yes. So, before I put the link of the feedback form for this session, can we all please turn on our cameras once? Yeah, everyone, turn on the cameras. I just hope I was audible and I was sufficiently conveying the thing. I asked everyone to please turn on the cameras.
Actually, madam, it's not. Oh, like I'm not able to have a control on that. Like, it's like loading. When I'm doing it, it's loading only.
But that's just for one person, right? I'm asking everyone. I'm not asking a single one. It is just my request to all the participants to please turn on your cameras as kind of a ritual that we follow every day, right?
Presentation mode, if you come out from presentation mode, it will be better, I think.
Yeah, Siddharth, if you are still there, you can stop sharing your screen, right? Yeah. Siddharth?
Yes, yes, yes.
Yeah.
I think I have come out from the presentation, right?
Like you can stop sharing if it is visible to you. You may stop, like press on the stop sharing.
It's been stopped, actually. I'm not sure why it is still. Is it visible?
Yeah, the last one is, at
Yes,
least
sir,
to
it's
me, it is
visible.
visible.
It's visible.
Okay.
Okay, it's gone, Siddharth. Yeah. I just hope everyone is hearing me and turning on, because those who have turned very much in time, I'm thankful to you. But we are expecting almost all of the people who have joined the meeting to turn on their cameras. Thank you for your patience. But please keep it turned on for a while, 2, 3 minutes more, so that all of the people may turn it on and we may capture it. Yeah.
Ma'am, can we turn off now?
Yeah, please, you can. Yeah.
Thank you.
In the chat that has been enabled today, I have just kept the link for the feedback for today's session. Is that link? Yeah, I just hope all are able to.
No, madam. Chat box is
The
not
link is not
visible.
opening.
No, chat box
Okay.
is not enabled.
Not visible. Yeah.
It's not in the chat box. It's in below the live captions. Okay, give me 2 minutes. Let me check it out.
Yeah.
It is not clickable also, ma'am.
It's not clickable.
No worries if you are not able to open this one from this chat box. I'll be sending the most conventional way, the way I have been sending for previous days. So let's not talk about it any longer in the live chat box. I got it. Okay. Now, do we have Bhavik with us? Mr. Bhavik, are you there? Bhavik?
Hello, good morning. Can you hear me?
Yes, yes, Bhavik. You are audible.
Okay,
You are audible to us.
okay.
So basically, before we start, I would just request you that once you check that whether or not you can share your PPT or not, and then I'll give your introduction and we'll start. Okay?
Sure, let me try that.
Yeah, yeah.
Excuse me, ma'am. Please close this real-time text, ma'am. Half of the screen is occupied by that only.
Can you see my screen?
Yes, your
Yes.
screen
Yes.
is
Yes.
visible. Yeah.
Okay, okay, cool.
Okay.
So okay, let me stop sharing and then you can start.
Okay. I would introduce you first and then we'll formally begin the session. Okay?
Sure.
Ma'am, can you switch off that RTT?
Yes, yes. I took your message. I got it, right? I'll work upon that. Give me 2 minutes. Okay? Yeah. I got it that you are not able to see the full screen and yeah. Okay? Yes. For us, it is a good evening, but for Bhavik, it is a good morning, right, Bhavik?
Yes, it is.
So across the globe, thanks to the technology, we are obliged to have Bhavik with us. He is from Austin, I guess, right? Austin, Texas.
Yes, yes. I'm
Yeah.
currently based out of Austin, Texas.
Okay. And we are so grateful to you for that despite of your work schedule and the timeline, you have joined the meeting and we are looking forward, very much looking forward to have your knowledge sharing with us, right? Thank you, Bhavik.
Thank you. Thank you so much
I'll
for
quickly
having me here.
introduce our next speaker of the session, Mr. Bhavik Chauhan. Uh, he has completed his bachelor's degree in engineering from Gujarat University, and after graduation, he has begun his career in semiconductor industries with e-info chips. Uh, for more than 15 years, he has the experience of working with ASIC physical design domain. During that time, he has worked with several leading semiconductor companies, including AMD, Qualcomm, Synopsys, and Intel. He has executed and delivered a broad spectrum of designs, including mobile CPUs, application processors, networking chips, server SoCs, and test chips across technology nodes from 28 nm down to advanced 2 nm. Over the course of his career, he has executed and successfully tapped out more than 15 chips. His core expertise is in driving aggressive PPA, that's power performance and area optimization for high performance designs, especially in the presence of complex multi voltage and power intent constraints. A significant part of his work has focused on timing closure, power optimization, clocking strategies, and place and route methodologies for deeply scaled technologies. He also has
Yeah.
extensive hands-on experience with industry-standard EDA tools, including Fusion Compiler, Invoice, Design Compiler, Primetime, Red Hawk Apache, Star RC, Formality, and Conformal, which are some of the few that he has hands-on experience with. He'll be sharing today the practical industry-driven insights into the ASIC backend physical design flow with an emphasis on real world challenges and design trade offs. Uh, so, uh, I feel great about all the achievements and his work experience. Welcome aboard, Bhavik.
Thank you so much. Thanks for having me
And
here.
yeah, and just a little thing I would like to share with all the participants that earlier session was also the design flow, and this one is the design flow as well. But believe me, both the representatives they had the understanding and they have tried their best to make them miles apart. Their sessions would give us everything new, right? So with that assurance, let us start with the second session. Over to you, Bhavik.
Thank you so much.
Yeah.
Let me share my screen.
For sure, for sure.
Okay, so hello everyone, and thank you, ma'am, for the introduction. I'm very honored and privileged to present on this forum. And so the today's topic for this session is physical design flow and PPA optimization. So PPA is nothing but power, performance, and area. Um, I am aware that the previous session was on the similar topic, but I have tried to make it little bit different, and so that you can get a new information or same information, but in a different way. Okay, I'm just trying to give you a different perspective on the physical design flow and the PP optimization topic. Okay, so with that, let's get started with the today's presentation. Uh, Something wrong. Okay. So here's an agenda for today. First, we will see what is the physical design field, what we do in that. Then we'll go through some of the basic stuff like what is PPA, triangle, and a couple of STA fundamentals. We are not going to go too deep into the STA because it's a huge topic. As a matter of fact, each bullet here it's a huge topic, and the topic itself will take 2 hours each, right? So I have tried to keep it brief and convey the message as to what we do in this each stage. So then next stage is a floor planning stage. That's where our actual backend flow starts, and then we'll go through the each stage like synthesis, placement, CTS, routing, Then we'll also cover some of the post-route optimizations and ECO closure. And then we'll end our session with few important sign-off checks and what are the impacts of AI and ML as of now on the physical design field. Okay, so where does the physical design fits into the whole ASIC design cycle, right? Uh, our ASIC design cycle starts from the design concept, right? So basically, it comes in the form of a specification based on the current market requirement. Based on that, the chip architects they create a design specification as to what frequency my chip will be running, what technology it will be implemented on, what are the power constraints, how much. So when I say power constraint, what is the maximum power that it can consume within some certain cycle or some period, right? Uh, and the area constraint, right? Like how much big or how much small my design or my chip should be. So it starts from there. Then the RTL designers, who are basically a front-end designers, who basically converts that design specification uh, into a high-level description language, which is nothing but an RTL code. Then the verification engineer verifies the RTL, whether the the functionality of the RTL code matches the specification, design specification or not. One important part that I think I missed in the design specification, apart from the selection of technology, power requirement, uh, what are the features that you need to code? What depending on uh, the domain of the chip, they decide the functionality of the design basically, but the RTL designer is the one who codes that concept into the actual hardware description language. So the next step is functional verification, where we verify the functionality of the RTL code, whether we were able to uh, implement the functionality which was conceptualized by the the design architects or not. From next step onwards, from the logic synthesis onwards, our physical design domain starts. Now, this is a little bit gray area. In certain companies, or a few years ago, right, like 5, 6 years ago, where the logic synthesis was not a part of a backend domain. Now, with the advancements in the tool, like the Fusion compiler, where we have a physical aware synthesis, and synthesis is basically a part of your placement and optimization. So that is the reason I've tried to cover the logic synthesis also here, because there is no real boundary between synthesis and place and route right now. All the physical design engineers are expected to do or perform the synthesis as well. So these are the steps inside the physical design domain. It starts with logic synthesis, then we take the design through place and route. Then we perform timing sign-off. Timing sign-off is nothing but whether my chip will function on the silicon on the desired frequency or not. That is basically a timing sign-off. And then at the end of the cycle, we perform certain physical verification checks uh, to basically check the manufacturability and the reliability of our layout. And once that is done, we have a complete GDS2. GDS2 is nothing but a layout format, and then we ship that layout to Foundry to get it manufactured. With that, let's move to the next slide. So what is physical design, right? I mean, to give you a brief introduction, it basically transforms the RTL into manufacturable chip layout by placing your logic cells, your standard cells, in a certain boundary, and it connects those standard cell according to your netlist connectivity. Uh, so it does all these things while making sure that we are meeting all the timing, power, and area goals. So I have tried to show a similar thing here. So the first box here is your RTL code. Then synthesis converts it into the gate level netlist. And once you go through the place and route, you have a complete layout as shown in the final picture. So, what all steps are involved in the physical design flow, right? So we start with the floor planning where we basically create a design boundary. Uh, and within the floor planning step, we also create a power delivery network. We'll go through each and every stage in a bit detail, but here I'll just take you through the steps in this slide. Uh, the next step is synthesis, where we basically convert the RTL code and map it into the technology dependent libraries. And then that basically gives us a get level netlist. And then we uh, forward this gate level netlist to the placement and optimization, where we place all the standard cells in your netlist according to its connectivity and timing constraints. Uh, then we perform a clock tree synthesis. And post clock tree synthesis, we perform a routing. Routing is basically connecting your signals with actual metal wires. Uh, and post routing, we also perform some kind of a post route optimization. And then we get into the ECO cycle. I have mentioned ECO only once, but it's a repetitive cycle we need to perform until we close the timing and other things like uh, power, IREM, all this stuff, right? Uh, and then we finally end the cycle with all our sign-off checks. When I say sign-off checks, it includes timing as well as physical sign-off checks. Okay, so let me give you some background on what is STA and few basic checks involved in the STA. So what is STA, right? It's basically a complete and exhaustive verification of all the timing checks in the design. Uh, Essentially, what we are trying to say here, right, is what we are trying to check here is whether my chip will run at the given frequency under the worst conditions on the silicon or not. Okay, so we will need to make sure that the frequency that the design architects had in mind during the concept of the chip. Are we able to meet those frequency requirements or not? So to check that, we perform STA on any given design. Now, why it is called STA, right? I mean, the static the term static is because it does not carry out the full blown simulation with all the vectors involved. It is actually a very exhaustive mathematical calculation to check whether we will be able to perform on the frequency which was perform on the desired frequency or not. Okay. So how does when we perform STA checks, right? The we obviously we use EDA tools like Primetime and Fusion Compiler, Innovus, etc. Right? Uh, so how does it performs this analysis? So first of all, what it does, right? It creates it uh, uh, divides the design into certain nodes, right? So here we have the primary input one, primary input two, and primary output one. Uh, so all the primary inputs and outputs, all your sequential in your design, let's consider them as nodes, right? uh, the tool basically divides your whole design into the timing path. Now, what are the timing paths? So, timing path is a complete connection of your logic from one node to another node. So, for this path one, uh, the whole connectivity from PI1 to D pin of the flip flop 1 is considered as a path 1. Now for this path from flip flop 1 Q pin to FF2 D pin is considered as path 2. Now uh, uh, this is how it converts the whole design or divides the whole design into timing paths. So I hope that I'm able to make this clear. Let me move to the next slide. So these are the two basic checks that we perform at almost every stage in our design, the setup and hold checks. So what is a setup check, right? Uh, Setup check is basically a check that ensures that the data which is launched. Just a second, let me. Yeah. So a setup check is basically a check that ensures that a data which is launched from flip-flop 1 on this clock edge can be it basically reaches flip-flop 2 and becomes stable before the next clock edge arrives on the flip-flop 2. Okay. So what we are trying to say here essentially is before that, what can prevent the data which is launched from flip-flop 1 uh, to be to get delayed or not reach on time on D pin of the flip-flop 2, right? So there are many factors here which are involved which can delay the data from Q to D. One of the factor is the clock to Q pin,
Bhavik,
clock to, yes.
Bhavik, so sorry to interrupt you once.
Mhm.
I'm getting the messages that people are not able to see the slides or PPT. So
Okay.
I'm just trying to verify once that
Okay.
how many of
Can
you
I
are
stop
facing
and
that issue. Yeah, if you can do that, that would be also great. You stop it and share again. That probably
okay,
could.
let me try that.
No, ma'am. Actually, a PPT is visible. Everyone is
It
talking
is
about
visible, madam.
you.
Yes, yes, ma'am. I know you all are talking about the captions, but some of the people
That,
also give me the feedback that it's about PPT. That's also not visible to them. Okay. So I know, but in caption thing, I would like to tell you that it has not been started by us, but whosoever has started it, till we are all in the meeting, it cannot be closed. You are getting me? I've Googled it and I'm seeing the videos how to stop it, but I'm unable to stop that.
okay, ma'am. It's okay.
Right. So tomorrow, there are certain settings on meeting side. Before beginning, I will apply them. Right. Today, I am helpless. I'm
Excuse me.
trying my best, but it's
Excuse
not
me. Can I
possible.
share something?
Yes, please.
Yeah. You can minimize this RTT, and then your whole PPTs will be online. I mean, it is a full screen. So if you minimize this RTT, will no problem. There is an
How do
option
we?
that you can minimize it.
Not all of the people are getting it. Can you also guide us that how to minimize? Because we are not getting that
You can
option to
you
minimize.
can see there is one
There is
diamond
no option
arrow
for me to.
diamond arrow near to live caption. Click to that arrow, live caption, open live caption in new window. Live caption, and in front of that there is one arrow. If you click to it, it will open a new outside, and you can minimize it. Then it will disappear. That window will disappear.
Maybe it is different from the versions to versions. Not
Yeah,
all of us
it's
are getting
possible.
the error there.
Those who
Yeah.
are using web browser, probably they not able to move it, but those are
Yes.
using Windows app, they can move it, or they can
Yeah.
remove it.
Yes, I am using through browser and I'm unable to move it. So people like me would not be. But try to concentrate on the content, right? I would request that. And Bhavik, have you reshared? Now, if anyone is not able to see the PPT, only PPT I'm asking, then please do let me know. Else we would continue the session. Is there anyone who's not able to see the slide? It's setup and hold checks. The slide is showing setup and hold checks. Are you all able to see that?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes,
I
ma'am.
just
It's
hope
visible.
it's visible. Okay.
Yeah,
And
it's
Bhavik,
visible.
Mm-hmm.
if it is possible, if
Mm-hmm.
you can a little bit like, how should I say it, zoom in, if just in case you may, then try, or else
Mm,
it is fine for us. Or else,
uh,
yeah, but then it will all go like, okay, fine,
yeah,
let it
because
be, let that be. No worries,
okay,
no
is
worries,
it
right?
too small for you to see, or
No, no, no. There's another issue. It's
Fine,
real-time
it's fine.
text has been enabled somehow.
okay,
So that
okay.
occupies the. But anyway, do not spoil anything of the presentation, right? Carry
Mm-hmm.
on. Yeah,
Okay,
yeah. We'll
okay,
concentrate more on the content. Yeah.
okay, sure.
Thank you, everyone. Thank you.
Yeah.
Yes, ma'am. Thank you.
So, coming back to setup check, right? So we were discussing what can delay the data which is launched from flip-flop 1 to flip-flop 2. So there are many factors which can affect the data to not reach on time to the next flip-flop. One of the such one of those factor is clock to queue delay, which is T to TCQ. Another factor is the combinational logic delay. Now, when I say combinational logic delay, the cloud that you see here, consider this cloud as a bunch of the logic gets connected sequentially, right? One after each other, one after another. So these are your combinational logic delay, and then the net delay. So uh, to connect this combinational logic, we need to have something called a net. A net is the one an entity which connects combination any cell from previous cell output to the current cell input, and this nets will are nothing but when you convert it into the physical layout, it basically is metal layers or metal wires, and these metal wires will also have its own delay. So that is another factor which will affect the data arrival time uh, for the D pin of the flip-flop 2. Now, to put it into the equation, what is setup check is basically uh, your T arrival max, right? So the time at which the data arrives on the flip-flop 2, it should be less than or equal to the time period. Because why time period? It's because we are checking the setup at the next edge. Okay, so time period minus T setup. So T setup is nothing but the setup time of the flip-flop 2. Uh, and it's basically a this sentence, right, where we say the data should become stable before the arrival of the next capture edge clock. So there is certain time before the capture clock edge arrival before which it has to be stable, and that is your setup time minus uncertainty. Now this uncertainty factor is before CTS, it is divided into two parts. Your first part is basically skew, and the second part is jitter. So skew, what is skew? Skew is basically a difference in the arrival time of the clock at uh, flip-flop 2 and flip-flop 1. So let's say this clock, let's consider this clock, right? And this buffer has a 10 picosecond delay. And um, let's say the net delay here is 0, okay, just for the sake of understanding. Uh, so the clock is reaching at flip-flop 1 at 0 picosecond, and since the buffer has a 10 picosecond delay, the arrival of the clock at the flip-flop 2 clock pin is at 10 picosecond. So the skew between flip-flop 1 and flip-flop 2 is basically 10 picosecond. That is nothing but your clock skew. Now, let's quickly cover the hold check here. So hold check basically ensures the data which is launched by flip-flop 1, it does not arrive too quickly on the flip-flop 2, so that it is not captured by the flip-flop 2 on the same edge. So basically, the data which is launched from flip-flop 1 should not arrive on the flip-flop 2 so quickly that it is getting captured by the same clock edge. And other thing is that let's say there is already a data present which is waiting to be captured on the flip-flop 2, right, from the previous clock cycle. So if the data reaches here too quickly, it will corrupt the data which is already present there, and basically you corrupt the data, right? So which is not something which we want in our design. So that is what hold check is. We can take some questions post session if you want. I know this is very complicated to be explained in one slide and five 2-3 minutes, but because it this concept itself, it took us like 4 or 5 months to internalize and get it right. So but yeah, you can in the later, I mean, you can Google it and try to understand it by yourself. Now the next and one of the most important topic in the chip design industry, right? It's a PPA triangle. So you take any chip in a semiconductor industry. Uh, it is the chip design cycle of any chip in the industry revolves around this PPA triangle. Right. So PPA, what is PPA, right? PPA is nothing but a power, performance, and area. Uh, Now, let's discuss each of this in little bit of detail, like what is it and why it is important. So let's start with the performance, right? So what is performance? So performance is nothing but the highest frequency at which your design can operate uh, on silicon, right? So we know why the performance is important, because day by day our workloads are getting very performance hungry, like it needs higher frequencies to run in today's day and age, where AI and the machine learning loads are becoming more prominent. The performance of the chip is of a prime concern for all the chip design companies. Now let's move to the power part of it. So Power, why it is important? We all know, we all use our mobile devices and handheld devices. We want our battery to last as long as possible, right? And for that to happen, our chip should consume less and less power. So the same thing, that is the reason why the power is very important in the chip design cycle. There are certain cases where you have a power sources next to your chip or your device, like the data centers and uh, the networking chips, where the chips are situated in the base station itself, and you have a power source very next to it. But uh, even in those cases, the power becomes more important, because more you consume power, more heat you generate, and then the more heat you generate, again, more energy you need to put it into cooling down the area and the surroundings of the chip, right? So that is the reason why power is becoming more and more important, and every chip design wants to get the highest performance for per unit of power which is spent. The next major factor in this triangle is an area. Now, why area is important, right? So area directly transforms into dollars. The more area you have, basically you have the more silicon real estate you are occupying, and the chip manufacturer will charge you more money to fabricate those chip with more area. So that is the prime reason. Cost is the prime reason why your area is very important. So as a backend PD engineer, your goal is to close the timing with minimum power and minimum area. So you'll certain cases it will be like you will have a power goal, uh, and with that power goal you need to close the timing with a minimum area. Depending on the chip requirement, your goals will vary. Okay, so but every optimization stage in your physical design cycle is a trade-off. If you try to improve performance, you'll pay it with the power and area. If you try to improve power, you'll pay it with performance. Not so much area. Area will improve, might improve. Yeah. Okay, so with that, let's get into the physical design. The flow. So our first step in this flow is a floor planning. Uh, so I have tried to give an impression of gradual information that we add, or gradual changes that we do in our design during floor planning step. So we'll start first with defining the core area or die boundary. So what is this core area or die boundary? It's basically area in which we will place our standard cell, and then we will connect those standard cells to create a layout. uh, now, what are the factors that we need to consider when we define the die boundary? One and the major factor that we consider is the utilization. Utilization is nothing but the amount of area that you have within your boundary, design boundary, versus the area of the cell in your netlist. So basically you try to keep this around 60 to 60. I wouldn't say 65, but 55 to 60% in today's cutting edge nodes, uh, before you start any optimization, because once you start the optimizations, it will add cells during the optimization, and it will increase your utilization. So you basically try to keep the utilizations somewhere above 50 and below 60, I would say. This can vary from technology to technology. Certain technologies like the Intel's back metal backside metal technology, where you can push the utilization to as high as 70, 70 to 75 ish. But it's better to start with the lower utilization. Okay. Now the next step is placing your IOs. So if you are a block level or a partition level engineer, most of the time you'll get the port locations from a full chip team. The full chip team is the team which basically divides your design into small partitions, and uh, it the partitions are nothing but small blocks within a chip. Okay, and these partitions will be implemented separately by a different partition owner. Okay, so in that case you will get it directly from the full chip owner. uh, in certain cases where the placement of these IOs are not favorable, it is causing some kind of a congestion or a timing issue, then you can provide a feedback to the full chip team and get it moved to a different location. Now, the next next step in the floor planning step is a macro placement. Now, for placing the macros, you need to follow certain guidelines. One part of or one category of the guideline is a guideline which comes from the technology manual. Uh, these are the checks like or rules like you cannot abort your macros at certain points or certain edges. What are the minimum distance you need to keep between the two macros, uh, and yeah, I mean the whether you can abort the macros or not. So those kind of rules, and then there'll be some uh, best practices you follow when you place the macros. Like you should not place the macros in the core region, right? You need to keep it clear for the standard cells to be placed. uh, you need to leave some certain amount of channel between two macros, or at the certain distance if you're abutting the macros, for buffering to, allow the buffers to be placed during the optimization. So those are the rules that you need to follow during the macro placement. And after macro placement, I think I've not mentioned it here because of the lack of space, but we also add some boundary cell, physical only cell basically. So few of these physical only cells are boundary cell and cap cell and tap cells. Uh, right. And then we end the floor planning step by power delivery network creation, where we create stripes uh, in our design. These are basically VDD and VSS metal shapes that we create. Uh, so this VDD and VSS metal stripes will provide a power to all standard cells in your design to function. Okay, so the next step we have in the flow is logic synthesis. So logic synthesis is nothing but a process of transforming the your high level design description into a gate level netlist, uh, and the netlist which can be physically manufactured on a semiconductor chip, right? So the first step in the logic synthesis is passing and elaboration. So passing and elaboration stage is nothing but when you read the RTL, right? So reading part is called a passing, and elaboration is where you uh, resolve all your instances module definitions. So basically, let's say there's a instance I1, and it is in the RTL, it is referencing it to some module M1. So we need to make sure that we are able to find the module M1 for instance I1. Okay, so that is nothing but passing an elaboration. And then the next step is technology mapping. So technology mapping is a stage where we where we map our logic into the actual technology dependent gates, right? We will discuss this in more detail. Okay, and then once we have a technology mapped RTL, we perform certain logic optimization to optimize the netlist better. So as you can see here, we have this RTL code where we are basically uh, create ending A and B and A and C, and then creating a OR between these two gates. So how does it transforms this logic into this gate level structure, right? So uh, it basically let's say you have A and B, right? So it goes to the standard cell library and checks whether are there any gates which has two inputs and performs AND Boolean logic. Uh, it finds that and takes it back and basically map your logic to that particular gate. Okay. So this is what I have tried to show here. So this logic gets transformed into this gate level structure, and then once you have that gate level structure, it will try to optimize it to make it more compact, and so that we can save less save on area and power. I mean, this is just an example, but certain times what you do, you merge certain gates to reduce the levels of logic, which will help you in timing. So, but in this example, we are saying that okay, we can transform this logic into this one to save some area and power. So this is what it is doing in the in the gate level netlist. I'm just trying to show the schematic here. This and this are same thing. So what are the outputs of the logic synthesis? At the end of the logic synthesis, we get gate level netlist and the design constraints. What do we check at the end of logic synthesis? So the first and foremost thing that you need to check are there are no unmapped logic, or there are no linking issues in your design. So every cell in your design should be able to uh, reference to the the standard cell which are available in your standard cell library. There should not be any black boxes. Okay. Uh, we basically at the end of synthesis, we also check zero wire delay timing. So why do we do this check, right? So and how do we do it? So basically we assume that all the nets in our design has a zero delays, which is not the ideal case, right? But uh, we assume that all the nets has a zero delay, and then we perform our timing analysis. Now, why do we do this? We do this because we want to see whether there are any deep logic paths in the design which can be become infeasible later in the design cycle when your actual RC comes into the picture, or actual metal delays comes into the picture, right? So basically to try and gauge the problems earlier in the design cycle. We perform timing problems specifically, perform the zero interconnect delay timing, and then we perform certain SDC sanity checks, uh, basically whether our clock definitions are proper or not, do we have proper exceptions in the place or not, how are our IO delays, if the IO delays are too high, it can affect your optimization. So we need to perform certain SDC sanity checks as well. Okay. Now let's move to the placement and optimization. So where your this is a stage where your uh, physical implementation starts, right? So so we start with a global placement. It is nothing but a course placement where uh, your basically initially what tool does is it just throws all the standard cell which you have in your netlist inside your design boundary. Now based on your connectivity of those standard cells and the type of tool constraints that you have given, it will try to incrementally switch the placement of the cell, and so the lot of this is where I mean I have given it mentioned is at a one stage, but it's a very highly iterative process that happens inside, right? So global placement is nothing but a very crude placement. At this place, after at the end of this placement, your standard cells will still be overlapping. It will still not be placed on the cell site and cell rows, and uh, you will have to legalize those cells. I mean, we'll come to like what is legalization and why do we need it later. So that is the first step of your placement, global placement. Once you perform the global placement, the next step is your hyphen out optimization. So during the hyphen out optimization, what we do is uh, we so uh, uh, after the placement, your standard cells are connected to each other without any repeaters or inverters, right? So buffers or inverters. So in the HFNS basically splits out the large fan outs into small branches. Uh, and we will discuss this in more detail. I have a good visualization of what exactly the hyphen out optimization does in the later slides. But to give you a brief idea, it basically breaks the nets, and uh, uh, is there a question? Okay. So it breaks the nets, divide the loads. That's it. Okay. Uh, and then we perform a global route. Uh, Global route is nothing but an estimation of it's a very initial stage of routing that we do for congestion as well as timing estimation. Now, this is just a placeholder for a global route. It happens a lot of times in the place of stage itself to after every iteration of every stage to estimate your congestion picture and your RC delays for every net. So just take this flow with the pinch of salt because it will be hard for me to put it into the visualization if I repeat this so many times. Okay, then we perform some kind of a physical level logic optimization. Now that your design is placed, you can better uh, you'll know it better that which size cells needs to be merged for a better timing optimization, and which can be cloned or which can be uh, remapped or restructured to better meet your timing or power or area goals, right? Uh, then we again perform incremental global placement. So I've used the global and course placement interchangeably, but it's the same thing. This is mostly to reduce the congestion which is occurred uh, because of the optimization that we perform before this stage. And then the last stage of the uh, placement and optimization is a legalization. So legalization basically removes the overlaps and aligns the standard cells to its site rows. Sorry. So goal here is to build routable placement while meeting the timing, uh, power and congestion targets. Okay, so just one more thing. So the global placement, there are two types of global placement. One is timing driven and another is congestion driven. In the next slide, I have covered the timing driven placement, what it is and what it does. Uh, so let's move to the next slide. Okay, so let's cover the hyphen out synthesis first. So, what is hyphen out synthesis? Let's say you have a long net which is driven by an inverter, and it's going to one of the inputs of this 10 AND gates. Now, since the net is long and it has a very high fan out, the capacitance of this net will be high. And the more the capacitance of the net, more it will, the transition time will be more for this net, right? Uh, so how do we fix this? So that's where the high fan out net synthesis comes into the picture. It basically, as you can see here, it first breaks the net and divides into the small parts. It adds the repeaters here, as you can see. These are the buffers, or you can also call it repeaters. And the other thing is it also divides these loads. So every standard cell will also have its something called input capacitance, and that will also contribute to the load which is driven by this driver. Okay, so to reduce the capacitance of the net, we also need to divide the load uh, in order to improve the transition. So as you can see here, a transition before the hyphen out synthesis, let's say there's just some random number that I have taken. Don't take it too seriously, but just wanted to see what happens to transition before and after hyphen out synthesis optimization. Okay, so this is what HFN is all about. Let's move to the next slide. So I have tried to show visually like how the timing driven course placement happens. Uh, so let's consider this as a path from flip-flop 1 to flip-flop 2. It goes through the C1, C2, C3, C4 registers. Uh, Now this path, as you can see, it's very well spreaded across the design. Uh, so when your path is too long, your RC, your wire length, and because of the wire length, your RC will be more, and that will contribute to the overall timing path delay, right? So the data which is launched from here takes a lot of time to reach to flip-flop 2. Okay, and it may not arrive before the next clock edge on flip-flop 2, and that will basically create a setup violation, right? Uh, so how does the tool fixes it, right? So it basically does a timing driven placement wherein it brings all these cells which are connected through a timing path close to each other. Okay, and it will place something like this on the next frame. So the goal is to the reduce the path wire length Once you reduce the violence, it will reduce the delay and it will improve the worst negative slack for this path. Now, similar thing happens in the congestion driven placement, but in the opposite way. Let's say this is a starting point. The second picture is the starting point of your congestion driven placement, right? And let's say this area is bit congested and you don't have enough routing resources to route all these nets, so it will start spreading this path a little bit to make make a resource available for this nets to be routed. Okay, so one of the most important checks that we do is a congestion check at the end of placement and optimization. So to understand the congestion, we need to understand how the global route works, right? So global route is the utility or a thing which estimates your congestion, estimates the congestion in your design. So how does it do it, right? So first, it divides your whole design into a very small boxes called GRC. So GRC is nothing but global routing cells. Okay, these are like a virtual boxes. It just divides internally into these boxes. Now, each boxes, let's consider this as a one. This is a zoomed in view of one of the GRCs that I've tried to show. Uh, let's just consider this is a only one layer, and let's say there are the dashed line that you see are the metal tracks. Uh, and so metal tracks are nothing but you can consider it as a lanes on which uh, you can drive the car. So you can, yeah, take a analogy of number of lanes on the road. Uh, Whenever you drive on the road, you drive on the only on the lanes, right? So the tracks are nothing but a lanes for the metal shapes to be routed or placed. Excuse me. Just drink some water. So let's take an example of this GRC where you have total 5 tracks passing through this GRC, and let's say this point you have only 3 nets which are assigned to this GRC. I have this in this for the better understanding. I have tried to show the metal shapes, but during the global route there are no metal shapes. There will be something called G links, which are like very thin lines which is connecting to each other. But this is just to so that we can understand it properly, right? So here we have 5 tracks available, but we have only 3 nets which are passing through this GRC. So this will be considered as a low congestion GRC where you have more supplies and less demand of the tracks. Now, on the right side, where you have 5 tracks, but we have 7 nets which are passing through it. So nets I've shown it in the shape of metal. Now, since we have low supply and high demand of the shapes, this cell will be considered as a high congestion GRC. Now, based on the supply and demand factor of each GRC, uh, it will be color graded, and the GRCs with high congestion will be colored in the very like the dark red, and the GRCs with low congestion or uh, the let's say it's barely supplies barely meeting the demand. In that case, it will be colored in the blue. Okay, so that's how the heat map for the whole design will be created to estimate how is the congestion in your design. Okay, so this is the last part of our placement where we perform a legalization. So what do we do in the legalization, right? Uh, we basically try to place standard cells on the cell sites, uh, and we need to make sure that there is no standard cell in your design which is overlapping with another standard cell. Uh, now, there are other factors also in the new technologies where uh, you need to align your standard cell pins to a proper track. But I think if it we will not cover that here because it's a again will be too long session to if we cover those things. Okay, so again coming back to PPA knobs, like how do we tune, what are the knobs that we can tune to improve each factor, like from the power performance and area during synthesis and place opt. So let's start with the performance. We can do logic restructuring or remapping to reduce the logic depth. Uh, we could also do retiming to balance rest to rest path. So basically, retiming is nothing but shifting a register across the combinational logic to balance the logic. Hello. Um, is there a question or can you mute yourself? Someone is speaking or not speaking. Okay, let me continue. Uh, the next thing that we can do to improve the timing is use a low VT cell or high drive strength cells on the critical paths. Now, using the low VT and high drive strength cells comes with a uh, with basically it will degrade your power because low VT cells are more leakier cells and it will have high power, so high leakage power. Uh, and high drive strength cells are basically bigger cells. The bigger the cell, more energy it will consume. So again, it will cost you power. The next thing that you could do to improve timing is path grouping. This is kind of a tool option where you provide a start point and end point pairs to tool to optimize those start and end points with more priority, right? Basically, all the placement and optimization stages in the placement flow will give more priority for this path to be fixed. Okay, now I have not covered. These are just a few examples of things that you could do in at this particular stage. There could be many more examples or things that you could do, but I've tried to keep the knobs limited here. Uh, the next thing is like, okay, let's cover the power. So how can you control the power? So you can add a clock gating to your design. So when you add a clock gating, let's say you know that at certain point of time a part of your design is not being used or it's not functional. What you can do is you can uh, stop propagation of the clock to that portion of the design. Okay, so as you know, clock is the highest switching net or a signal in your design, right? No matter what happens, the clock will always be switching, right? And with more switching, uh, it consumes more power, right? So if the certain part of a design is not functional and at certain point of time, you basically stop propagating a clock onto the sequential cells of those in those part, right? So that basically saves your switching power. Next is multi-bit flop. Multi-bit flops are basically when you merge multiple flops into one flop. Uh, that can also help you reduce in power, and it, it will help you reduce area as well. But will So how does it reduce the power, right? Uh, so let's say you have four single bit flip-flops. When you design a clock for this four single bit flops, you need to have a separate trees created for all these four single bit flops. When you convert this four single bit flops into one multi-bit flops, uh, your clock pin will only be one. It will be internally connected to all the single bit flop clock pin. So that's how you, I mean, it's not always the case, but it will save you a lot of power by reducing the clock buffering with as compared to when you have a single bit. Okay, and then you could use high VT and low leakage cells on the on non-timing critical paths, and then you could enable safe-based optimization. So safe is a switching activity file that we feed it to the place and route tool. Uh, to let it know that okay, this my instances are switching at this point of time, and based on that switching activity information, it optimizes the design better for the power. Yeah. Next is area. So how do we improve area? uh, Not much we could do as a user apart from guiding a tool to perform high effort area optimization. Uh, and we could use high density standard cell library. So these are like a smaller cells, but again, to get a performance out of these library cells, it's very tough. So uh, if your area is your primary target, you should use this. Okay, so let's jump right into the CTS. So what is CTS and why do we need CTS, right? So CTS, so clock is the very important signal in your design, right? All the other signals are timed or function with respect to your clock. So, so that is the reason why a good distribution of this clock signal is very important, because if your clock reaches a different point in your design or different flip-flop in your design at different times, it could cause a lot of disturbance and timing violations in your design. So CTS is the process that builds a clock distribution network from your clock source to all the sequential elements like flops, latches, and macros. It basically inserts buffers and inverters. Uh, yes, ignore the clock gates. It doesn't insert the clock gates. Clock gates comes as a part of RTL, so we don't do that. To basically create a balanced clock tree, right? And why do we need CTS? It's basically by default your clock before CTS, your clock is ideal, uh, and it's directly connected to from port to your sequential cells, right? And since the net are too long, there is a very high fan out. It basically has a very high RC delay, and as I said earlier, the arrival times at every flop will be very uneven, and it will have a very high transition. So what are the key targets of the CTS? Uh, the first one is a slew. Uh, so basically, we first thing that we do when we build the clock tree, right, is make sure that we the transition on every segment of the net is well within the range, right? So we try to improve the slew or a transition time, and then we try to improve the latency. Uh, so latency is nothing but time taken for the clock to reach from your source, basically a port, a clock port, to the flip-flop clock pin. That is nothing but your insertion delay, and we want this insertion delay to be as low as possible. Okay. Uh, Clock skew is one of the targets. So clock skew is basically a difference in clock arrival between two flip-flops. Now, the clock skew, it used to be a very hard target in past, but with the introduction of concurrent clock and data optimization, where we use clock skew to push certain flops to uh, meet the timing. The clock skew has it's not so much important right now for as a key targets, but again, certain cases you need to meet clock skew as well. And the last is clock power. So since clock is a highest switching net in your design, right, or signal in your design, uh, more the switching, more the dynamic power, right? So we and if you take a total power and clock power as the percentage of a total power, it's a significant amount. So that's the reason why we want to make sure that we can build the clock tree with as much lower amount of buffers as possible to reduce the dynamic power. Buffers or inverters, you can, based on the cells that you're using. Okay, so this is just a visual representation of how CTS works. So before CTS, your clock source is directly connected to the clock pins of the flops, and once a CTS happens, right, it basically try to add buffers and repeaters to improve the transition time, and then once that is done, it will try to balance the tree so that let's say this is a flip-flop 1 and this is a flip-flop 2. So the idea is that it should reach the clock should reach both on flip-flop 2 and flip-flop 1 and flip-flop 2 around similar times, right? Should not be too much difference. So uh, so that is the biggest difference between HFN and the clock tree synthesis, where HFN doesn't care about the balanced tree, whereas CTS we need to have a balanced tree. Okay, so what are the PPA knobs that we have in CTS? Skew target, tighter the skew, better the setup margin. But as I said earlier, it's again with the introduction of CCD, the skew targets are kind of not so much important. Uh, so next point says that the use of concurrent data, concurrent clock and data optimization to use the skew for better timing. Uh, your latency and insertion delay targets basically controls the clock arrival time, slew and transition time, transition targets keep the clock edges sharp and predictable. Variation aware CTS, I think so. The variation over CTS is basically you try to keep the common path as much as long as possible to reduce the variation in your clock tree. So what are the power knobs? The label, the buffer and inverter count. So use as low as possible buffers and inverters as possible to reduce your clock power. Cell selection. This is very important. So it uh, if you use very leaky cells, your clock CTS quality will be very good, but uh, the the variation for this low leakage cell is very high, and it's very uh, high across the different scenarios or corners. So you want to make sure that you choose the right VT cells when you build the clock tree. Uh, I think the other two things are self-explanatory. So, and for the area knobs, again, it comes to the less buffering. So we want to use as low, as many lower buffers as possible to build the clock tree. It will also help us in area as well as in power, right? Avoid oversizing. We should not unnecessarily oversize the clock tree drivers to, you know, fix the transition on up after some limit, right? And use shared buffering wherever is possible. The shared buffering part will also help us in the variation of a CTS, right? Where more the common path, more you avoid the variation on the clock paths. Okay, so the next step is routing. So routing basically happens in three stages. Uh, it starts with global route, then it does a track assignment, and then it does a detail route. So as you can see, global, we are again facing the same topic, like global routing. Uh, so as I said earlier, right, there are many steps in the flow which will be repeated multiple times iteratively to improve your design performance. So global route is one such a step which is repeated n number of times during your physical design flow. But this is the last time I think that it tool will perform global route, and this is for the final routing. So at this stage, it creates a route through GRCs. Basically, it assigns your nets in a particular GRC to estimate the routing demands and capacity. Uh, then the track route happens. So track route or a track assignment, it basically lays your signal on the preferred layers and the tracks based on the estimations given by the global route, right? Now, at this stage, your nets are not fully connected to each other. Your It is just a rough routing that tool has done. That will be done in the next stage during the detail routing. So detail routing is the stage where it creates end-to-end connectivity for any particular net, and it also is DRC aware. When it does detailed routing, right, it also checks what are the DRC violations that this net has with respect to the neighboring shapes, and in the subsequent step where it does search and repair, it basically fix those metal DRCs and while keeping the connectivity intact. Okay, so once your routing is done, that means your design is fully connected. All the metal layers, metal shapes are there in the design, providing a connectivity from one cell to another, right? Now that you have actual metal shapes, right? Uh, it basically can degrade your timing. It basically generates a final RC parasitics. These are like a final what you see in the layout, right? Uh, and whatever timing that you see, like the net delays that you see before routing are just an estimate. And what you see after routing are the actual RC delays that you will have on your actual silicon. So there are advancement in tools to make the estimation better before routing, but we still have a huge gap on estimated timing RC delays versus the actual RC delays. That you can consider it as a tool limitation for now. It's there in all the major EDA tools. So whenever you go from pre-route to post-route, you will see huge timing degradation. Now, how do we fix this timing degradation? So tool basically performs one more round of post-route optimization to recover the timing. So what does it do, right? It basically performs the similar stuff again in few iterations to whether upsize the cell, break the nets, buffer the net, uh, and improve the timing, right? So that's what the tool does. Now, even after the tool based optimization, your timing will not be fully closed. So that will require some user intervention, and that's when your job comes in, where you will be manually writing ECOs to improve the timing, transition. Uh, in timing, you will fix setup, hold, all the stuff, right? So the basically this is an ECO stage where it's a iterative process where you uh, write the ECOs to upsize the cell, add the buffers manually. Basically, whatever tool has done automatically, like uh, in the flow, you will be doing it manually here in this stage. And this is like you'll have to do based on the violations that you have at the end of post route optimization. You have to do 10-15 iterations if required. Okay, and then again you feedback this user written ECO. So user written ECO is nothing but a command given to tool to upsize certain cells, downsize certain cells, or add the buffers. So after the changes are done, right, you will also need to perform one round of ECO routing. So ECO routing is nothing but very small changes in your routing connectivity that you perform without disturbing the other nets in your design. Okay. So this is what the post-route optimization and the ECOs, timing ECOs is all about. Now, apart from the timing ECO, so, okay, sorry, my bad. I forgot to mention what ECO is, right? So ECO, the full form of ECO is engineering change order, okay? And so apart from timing ECO, we also have sometimes a functional ECO. Let's say uh, you are already in the physical design cycle, and that the design architects finds out that okay, certain functionality is uh, not performing, or not certain part of the design is not functioning as per the intention, and they want to add certain logic into your design. So in those cases we will have to perform functional ECO. Now the functional ECO part is taken very selectively. If it is a very big change, then we will have to go through the whole place and route cycle again. If it is small, you can consume it later, and like few hundreds of cells, you can consume it directly as an ECO. Otherwise, you'll have to perform the whole place and route cycle again. Okay, and this cycle you in one project cycle, one design cycle, you will iterate through this process, like from synthesis to routing and post-route optimization, let's say, uh, hundreds of times for only one design. Okay, to get a timing closed routed design. Okay, so this is not a one-time thing. We do this every day, day in, day out, to close one design and to get the design into the shape where it is meeting timing and it's routable. Okay, so let's quickly cover the design, few of the sign-off checks. One of the very important checks is DRC. So DRC is nothing but a design rule check that ensures the physical layout follows all the foundry rules, so that it can be fabricated reliably by the manufacturers, by the foundry, right? So these are some of the rules that uh, we we see and we fix it in the design. Uh, Minimum width, minimum spacing, minimum area, wide metal jog, notch spacing, end of line spacing. And here I have tried to show what the violation is all about in each of these pictures. So let's take example of this uh, thin and fat spacing violation. So what this violation is basically that so on the right side you have a regular width wire, and on the left side you have a fat metal wire. So there should be some requirement in your rule deck which comes from your foundry, that if the fat metal uh, sorry there should be a minimum spacing required whenever you have a fat metal routed to the regular to very close to a regular metal shape. So how do we fix it? We basically increase the spacing between these two metal shapes. Okay, so these are just very few examples. There are hundreds of checks that are defined in the rule decks. Most of there are tools available which can fix some of these rules, but then it won't clean your design completely. So you will have people, who needs to fix this violation, and it requires a very much user effort to fix this violation. So sometimes in some companies you have a different group of people who will just be working on fixing all these violations at the last mile closure. So in short, basically, DRC rule checks are the checks that are in place so that uh, we we follow the foundry guidelines or foundry rules so that foundry can manufacture our chip reliably and without any issues, right? So next list in the sign-off check is layout versus schematic. So as the name suggests, right, layout versus schematic, it basically compares the extracted netlist from your layout. So it basically first takes your layout, it extracts the spice level netlist from your layout, and then it will compare it with your actual schematic netlist. So the actual netlist that you have at the end of a post route. And then it basically compares these two netlists device by device, nets by nets, ports by ports, and see whether there are any mismatches between the layout netlist and your actual schematic netlist. So why do we perform this, right? So we basically check during LVS whether my layout, the layout that I have implemented, whether it is the layout, the functionality of that layout, whether it matches my intended design or my netlist functionality or not. Right. So these are some of the examples of errors that we could see in the LVS. So one category of it is extraction error, another is compare errors. So extraction errors are nothing but the errors that you face when you extract the netlist from your layout, right? So some examples here. I'm not going to go too deep into this because, yeah, it's again a very big topic, and I think we are already running out of time. Okay. The next check that we do is the airdrop analysis. So airdrop analysis is nothing but drop in your voltage uh, because of the power consumed by the cells and the the structure of your power delivery network. So why does it matter, right? Uh, it basically when you have a drop in the VDD, right? Your standard cells get a lower voltage, and that basically slows down your cells. Now, slower the cells, the slower cells will affect your setup timing, right? So if your cells are slower, it basically delays your data to reach from one flop to another. So that will basically create a setup timing failures for you. And in certain cases, if the VDD drops too low, it can also create a functional failures. So there are two types of analysis that we perform in the airdrop analysis. One is static IR analysis and another is dynamic IR. So static IR is a vectorless airdrop based on the average current. And this is performed very earlier stage in the design where to basically determine the stability and the uh, stability of your power delivery network. And a dynamic IR drop is the activity based IR drop check where we actually propagate the vectors in your design to see the where the worst picking occurs, and at the worst peaks, how much air drop happens at certain parts of your design, right? So how do we, if you have air drops, how do we fix it? So strengthen your power delivery network, add more straps, wider metals, more vias, basically create more parallel paths and reduce the resistance of your power delivery network. Uh, You can also add decap cells. So decap cells are you can consider it as instantaneous power sources. So whenever, let's say during the peak operation, when the nearby cells draws more power, this decap cells could also become a source of your power, which can, provide instantaneous power to your power delivery network. Uh, then you could also do cell spreading, cell spreading to reduce the local activity hotspots. Okay, so I think this is the last slide. So this check is basically logic equivalence check, where we basically check the functionality of your design before and after every optimization stage. So what we check here is basically after every optimization, my design functionality is not changing, right? It basically confirms that there is no functional bug introduced while fixing timing, area, or power. Where it is used, as I said, after every major step in your design, you should perform LEC. So let me quickly cover these two slides. I think these are the last two slides. What are the AI ML feature in the modern EDA tools? So as you know, everywhere we are seeing that AR or AI or ML, right? Uh, but we are in physical design or domain. We are in very early stage of AI and ML adoption. I'll cover the reason in the next slide why it is so. But we do have tool options, mostly from the EDA vendors, where ML is very tightly integrated into the current design solutions itself, EDA solutions itself. So here are the few examples: reinforcement learning based V.P optimization. ML-based macro placement, DSOAI, I think I've already mentioned that. Then there are few EDA vendors who are coming up with AI chatbots. So if you need some help with respect to your EDA tool, you don't have to go to uh, your local AE to help, right? Application engineer to help for the help. You can directly chat with your chatbots and get a resolution from the chatbot itself. Uh, so what are the pros and cons? Okay, so let's discuss this little bit in more details. So when you use the solutions like DSO AI, right? Uh, it basically spawns of tens or hundreds of experiments with the different tool settings, right? It reduces the manual effort of tuning each and every tool options, and it saves the engineering time. And certain times there are certain tool options that you wouldn't even know. It could use those options to improve the QR, which otherwise would be very hard for you to find, or certain options that are hidden, it can use and improve the QR. So it can lead to faster convergence for the timing with a very few human iterations, but it comes at the cost, right? So the cost is compute and storage. So let's take an example of the design that I'm doing right now. It's a 2.5 million instance count design, and that design, it takes 150 hours, 180 hours to run, uh, which is almost more than a week, right? Uh, and it takes 16 core 300 GB RAM machine to run for 180 hours, and it occupies around 3 to 400 GB of disk space for one run. Now imagine a tool which let's say just spawns of 10 of such jobs, right? So imagine the number of resources that will be used, uh, number of disk space that we will be using, and this is just for one partition, right? In a any given project you have let's say 15 such partitions. So if you accumulate everything, the cost of the resources that we utilize, uh, it will be hard to justify compared to the gains that we get from the AI. So yes, the tools are evolving, and it might get us a better in a better flows or a better tools in future, but for now we are not, I would say we are not there yet, but we are there are progress, there is a progress which is happening with respect to AI and ML even in the physical design domain. So I think that was the last slide. I hope I am able to convey the message, and you know, you would take something away from this session. But it is very hard to uh, put the complete physical design domain in 1.5 hours into slides. But yeah, I hope I made the justice. Thank you so much for your time.
Yes, we understand that it is difficult thing to convey this stuff of a subject into just 1.5 hours. But really, really well. You were wonderful in your session. On dot, to the point, and it was very informative, hugely contributing. Thanks a lot.
Are there any questions? I
Yes,
can
yes.
take
Anyone is
questions.
having any query can surely ask right now. Query? Okay. So for a while, let us all turn on our cameras.
के बाद लाल सोर्स कर लूं या बल्ट करूं खाली ना मैं और
I guess not all of the people are responding to this. Please turn on your cameras before we end up the session and wrap up the day. It's just that fine. Thank you, Bhavik. Let's not
Thank you.
extend your time more than this because you may have a working and a busy day ahead.
No, we are good. I'm good. I mean, I've taken a half day off, so I think I'm good.
Oh, oh, thanks a lot for that
Yep.
concern,
Thank you
Bhavik.
so much.
Thanks a lot. Yeah, 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 yeah. Okay.
Okay.
We may
Thank you,
all.
everyone.
Yes,
Thank you,
thanks a lot.
Bhavik. Thank you.
Thank you.
Thanks a lot. Yes, so
Thank you.
we are ending the day for the day, and tomorrow again, sharp at 6 p.m. Would be ready with two more wonderful speakers. And I just hope you all are getting what you had aimed when you had thought of attending this FDP. I just hope the sessions are up to your expectations, right?
Yes, ma'am.
Thank you. See you all soon. The
Thank you very
feedback
much.
link, of course, I'll put in 5 minutes. I get more reminders of feedback links than anything else. Anyway, so yeah,
Thank you.
wish you all a good night and see you tomorrow. Thank you. Thanks a lot.
Yes. Thank you.
Thank you, madam.
Family.